Hi everyone, can you hear me? Okay, so just let me know if I'm audible. If everything is fine, audio, video, just let me know. Okay, great. So in this session, we are going to see synchronization. We will make sure that all the things about the synchronization is completely completed. Okay. So here in this session, I will make sure that all about the synchronization, whatever they ask in the synchronization should be completed. But before I get started, just let me know if audio, video, everything is perfectly fine or there is some issue. Okay. Just let me know. Okay. 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 Great. So let me just tell you that from this synchronization, okay, from this topic, there has been in past, I think, approx, okay, 30 years, there has been, I can say, there has been more than, okay, there has been almost, almost 55 questions, right? So what do you understand from this? It means that almost every year they are asking on average 2 questions per year. So hence it means that this topic is very very important, isn't it? So you can expect that after this session, you will be getting like this 2 questions might be from 2 to 3 marks, right? Sorry, 3 to 4 marks, 3 to 4 marks. So these 2 questions will be from 3 to 4 marks. So most probably there will be 2 questions this year also, and hence I can say that you will be getting 3 to 4 marks just after this session. Okay, so let's get started. Now the topic here is synchronization, right? Let me first define you that what is the synchronization problem, and then we will see that how to deal with this problem, right? So basically the synchronization problem says that uh, if there is some area, and that area is shared between multiple processes. Let's suppose these are the 4 processes: p1, p2, p3, p4. If this area is shared between multiple processes, then if all the processes or maybe more than one processes want to access this particular area at the same time, in that case there will be some problem, right? So what do I mean by that? Let me just define you from our very first example, which is one non-technical example that I want to take, which is of chef and bread problem. So let me just tell you that what is this problem. See, just assume the problem that you have here is something like this. Just assume the problem which is something like this, which is saying that you have some storage area, maybe kitchen or maybe something like this, right? You have your kitchen, and there is some list outside this kitchen that whether this particular item is available or not. For example, this bread packet is available or not in this kitchen, right? Let's suppose this list says yes, that this is available. So what does this mean? Let's suppose this is chef 1, chef 2. These both sees that okay, this bread is available, right? These both of the chefs sees that okay, bread is available. Then what this both of the chefs will do? They will check that okay, bread is available, and then they will go inside, right? And then since there is only one packet, then each of the chef, let's suppose, wants to access or wants to take one packet. Then how many chefs can take? Only one chef, right? Only one chef can take one of the packet. There is only one packet available, let's suppose, and this list is saying yes, bread is available, right? Now, what will happen in that case? Let's consider the scenario that these are the 3 steps that any of the chef perform, which means it will first check if the list has bread, then collect the bread, come out of the room, and update the list. So basically, these are the, let's suppose, 3 steps that any chef is performing. That first check that list has a bread, collect the bread, and come out of the room and update the list. Okay. So suppose let's just assume that this chef, okay, this chef 1 goes inside after checking the list. Okay, the list is saying the bread is available. So this step is done. Yes, bread is available. Then collect the bread. If we collect the bread and then come out of the room, then update the list. Then what will the bread? Then it will say no. Now the bread is not available because it has been taken from the chef 1. Now, what do the chef 2 sees? Chef 2 will say that okay, this bread is not available. Hence the chef 2 will not go inside, right? Hence will chef 2 will not go inside. So basically, one possible sequence of instructions could be this chef 1 goes and completed all the instructions, which mean all of these 3 chef 1 perform, and then Ceph2 try to perform, and then Ceph2 will say that, okay, see, bread is not available, I can't go. So this is perfectly valid. I mean, if after Ceph1, Ceph2 goes, then this is perfectly valid. But life is not that simple. I mean, there could be some intermix of the operations. It might so happen that Ceph1 is executing these two and this three, and in between these three, which means Ceph1 check that bread is available, and goes to collect the bread. And in between, Ceph2 also sees that, okay, bread is available, and goes to collect the bread. Now you tell me, in this kitchen or in this storage area, if I say that there is only one bread packet, then can you tell me, after these two steps of each of the chef, how many chefs are present here? Two chefs, right? Now let's suppose this chef one first perform this, that, okay, it collect the bread. Now suppose now after this chef one is collecting the bread. If chef one is collecting the bread and coming out, then tell me, can chef two, okay, can chef two collect the bread? The answer is no. So chef two will not be able to find the bread, which is inconsistent, right? Why that is inconsistent? Because Ceph2 has already seen that, okay, bread is available, right? The Ceph2 has already seen that bread is available. I mean, if both of the people are seeing that, okay, bread is available, and then both of them are going inside, then only one of them can get the bread, isn't it? So who will get? Whoever is first collecting. That is very simple, right? So basically this list is saying bread is available. So Ceph1 will think that, okay, bread is available, goes inside. Ceph2 will think that, okay, bread is available, goes inside. Now at this place there are two Ceph. Now one of them will collect and will come out, and another one is basically just surprised that why bread is not available, because list was saying bread is available. So that is the reason. I mean, this is just one non-technical example. don't try to very much relate it with the computer science, but this is just to motivate the idea. So here, if you have understood that, as per the Ceph2, tell me, is this fair? Because Ceph2 has already seen that bread is available, and then it goes inside and bread is not available, right? So as per the Ceph2, it is not fair. So that's why I'm saying it is inconsistent as per the Ceph2. Okay, there's an consistency as per the Ceph2. So let's just see this idea from one more non-technical example, which I'm calling the too much of milk. Okay, too much milk problem. Now, how I want to motivate this idea? Let's just see, right? So how I want to motivate? Let's suppose these are the two roommates. Okay, let's suppose let's suppose Sachin, and let's suppose Deepak. Okay, I and Deepak both are the roommates. Okay, Deepak. Okay, suppose I and Deepak both are the roommates. Then in this at this time 3 p.m. I will see, I will arrive home. I will look in the fridge that there is no milk, and I will leave for the grocery to collect the milk, right? At 3:20, I will arrive at the grocery. I will buy milk, and I will arrive to the I will arrive to the home and put milk in the fridge. So this is my sequence of instructions. And let's suppose when I left for the grocery, at the same time, Deepak is seeing that, okay, there is no milk in the fridge, right? There is no milk in the fridge, and Deepak has also left for the grocery. And then I have already put the milk here. Then by the time Deepak comes and try to put the milk in the fridge, see, I have already put milk in the fridge at 3:35, right? Now Deepak is going to buy, and the moment it try to open the fridge, and it will Deepak will say that, okay, there is already milk available. So as per Deepak, there should not be any milk, but there is a milk. So that's why again this is inconsistency, which I'm calling too much of milk problem. Right? Too much of milk problem. Have you understood that what is happening here? Let me know. Let me know. Is this clear? That this is also inconsistent state. Right? This is also inconsistent state. Okay, Akash Manji is saying it actually happened to me once. Okay, so you can say this is a real life problem, right? So yeah, this is a real life problem that this may happen. So what we should do? We should have a critical section here, right? We should have a critical section. So let's just see that, I mean, what I'm talking about basically. So basically, these things are called race condition. Let me first tell you that what is this race condition, and what are these solutions, right? So what may so happen? Let's suppose this is x equal to x plus 1, and there is a x which is a shared variable, which is initially, let's suppose, 50. Let's suppose these are the two threads or the two processes, maybe P1 P2 or the thread T1 T2 wants to execute this. What do you think once both of this is finished? What do you think the value of x will be? What do you think? What do you think the value of x will be once both thread finish? It seems like it should be 51 and then 52, right? But it is not always the case. Let's just see why. Okay, let's just see why. See what is happening here. What is happening here? There is a shared variable which is x equal to 50. It is just shared between two threads or two processes, right? Shared between two threads or two processes, whatever you want to say. Okay. So x equal to x plus 1. Let's suppose they are executing this x equal to x plus 1. Now, if this is shared between two processes or two threads, T1 and T2, right? T1 and T2. Let's suppose this is shared between two processes or two threads, T1 and T2. Then what's going to happen? Can anyone tell me? See, it looks like this is just one set of instruction, but actually in assembly, this is not one set of instruction. This is actually how many set of instructions in assembly? In assembly, this is three set of instructions. First you will load the value, then you will add, and then you will store, right? Let me know if this is okay to everyone. So you will load into some register, right? Maybe register I mean R1, and then let's suppose X is at memory location 1000. You will load into some register, and then you will add 1 to this, and then you will store, right? Maybe you can say that okay, this R1 should be stored in the location 1000 or something like this. So basically there will be load and store. So there are three instructions in reality, right? This is not just one instruction. So what may so happen, as most of you might be already knowing, so let me just quickly tell you that what may so happen, that instead of executing this properly, there could be mix of instructions, and by which there will be inconsistency. How? Let me just show you. See, it might so happen that this particular thread, right, T1, it may say that okay, it will first load the value which is initially it is 50, right? Initially it is 50, right? Now T1 is saying in this register I have loaded, then it will in this register only, it will basically modify that to 51, right? And then there is a memory location 1000. Now before it write to 1000, let's suppose there is a T2 which has already maybe the same register. I mean, doesn't matter, basically it will be the context switch, so the register value will be saved. And I mean, don't get confused. If you are getting confused with the same register, you can take the different register. Okay, so it may have also loaded 50. See, both of them may have also may have basically executed this particular instruction. So both of them may have loaded 50 only. Both of them may have modified to 51, and now this particular memory location is shared, right? Now whoever is writing first, let's suppose it is writing first, then it will be 51. If it is writing, then also it is 51. So what may so happen, that ultimately the value could be just 51, right? It may be 52 also if T1 is executing all of this, and then T2 is basically, it may be 52 also. How? If T1 is executing all of this, and then it is incrementing to 51, and then T2 is basically after it writes, then T2 is after it writes, then loading to this R1 this updated value 51, then it will modify it to 52, then it will write back, right? So basically it could be 52 also, it could be 51 also. So this is an inconsistency, right? Now since this is basically happening because of this shared variable, so that's why we need to take care of this particular region, right? Because in this region only it is happening, which means let's suppose T1 has a big code. Okay, this is a big code that T1 has. T2 also has a big code. Okay, which means T2 also has T1 has some code, T2 also has some code. Okay, let's suppose T1 has this x equal to x plus 1 here, x equal to x plus 1 here. T2 has it somewhere here, right? So basically this particular area only is some sensitive area. Otherwise if the things are not shared in these areas, then these areas are not sensitive area, right? So this area, can anyone tell me what is the name of this area? This area is called critical section. This is called critical section, isn't it? Let me know if that is okay to everyone. That we call it critical section because it is shared, right? So whatever we have to deal with the shared memory, it is called critical section. Okay. Now let's just do one thing. Now let's just see that how to deal with this critical section. So This is basically also called a race condition. Race condition is a condition in which several processes access and manipulate the same data concurrently, and the outcome of the execution depend on whether the order in which the access take place. Which means let's suppose there is T1 which is basically saying x equal to x plus 50, and T2 may be saying, it need not to say x equal to x plus 50, it can say x equal to x plus 1, and let's suppose x is 50 initially and it is shared between both of them, right? Both of them. Now let's suppose that T1 says that okay, it has in the memory x is 50, right? Let's suppose at 1000 location. Okay, now T1 may say that okay, initially x is 50, right? Initially x is 50. Now T1 may say that, let's suppose this is R2 and T2 is dealing with this. T1 may say that okay, let me load it. So T1 has loaded 50, then it will be 100. Now it has to write back, and let's suppose meanwhile it has also loaded 50 and this is 51. Now whoever is writing first, the final value will depend on that, right? Isn't it? If whoever is writing last, basically, right? So if T1 is writing first and then T2 is writing, then final value is 51. If T2 is writing first and then T1 is writing, then final value is 100. So whoever is writing last, the final value depend on that. So that's why it is kind of a race between T1 and T2, isn't it? It is kind of a race between T1 and T2. That race of being last, actually, who is basically finally updating this, right? So it is a race between T1 and T2. Hence it is also called as race condition. Okay. Hence it is also called as race condition. Is this okay to everyone? Let me know. Okay, great. Now, what could be the naive solution? Can you tell me? Which means if T1 is here and T2 is here, which is executing some set of instructions. Let's suppose it is x equal to x plus 50, or maybe x equal to x plus 1, doesn't matter, and x equal to x plus 1. And you don't want to have race condition. You want to solve the critical section problem. Like this is also called as critical section problem. So what is the naive solution? The naive solution could be that you force or you ask for sequential execution, right? Sequential execution. You ask for the sequential execution, but it is not that good. Why? Because it may be unnecessarily. Basically, let's suppose T2 is here doing some disk operation, right? And you are saying that okay, I want T2, let's suppose, or maybe T1 or then T2. Let's suppose that here T1 is doing the disk operations. Let's suppose T1 here is doing some disk operation, right? Now maybe the printf is one disk operation, some monitor operation, resources, right? Because it needs the resources. Now let's suppose it is printing, so you don't really need CPU. You could have scheduled T2, but you are saying no, I will schedule T1 once it is completely finished, then only T2, right? So T1 and then only T2. So this kind of things are not very good. I hope you understood why it is not very good. So I will say this naive solution is basically the sequential execution, but it is not good, right? So naive solution, as per the naive solution, you can say it is a sequential execution. It is a sequential execution. But it is not that good. Let me know, is this understood to everyone? Why this is not good? Because it is not efficient, right? Not that good means underutilization of resources. Underutilization of CPU. Is this okay to everyone? So we want to solve this critical section problem. I hope you understood that what is this critical section problem. What is this problem? The problem says that there is critical section means this shared variable modification. Okay, this particular section is called critical section problem. Yes, naive solution will lead to the poor utilization. So this is a critical section, and we want to solve it. What do you think? What is the very first thing that is coming to your mind? Okay, what is the very first thing? Which means critical section means multiple processes may want to modify this particular variable at the same time. So if T1 is having some critical section here, maybe x equal to x plus 50, Tell me, should T2 be having the same kind of modification, or T2 can have anything else with the x? Maybe x equal to x plus 1, right? Let me know. Let me know. Is this okay to everyone? X equal to x plus 50 and x equal to x plus 1, right? Now you see here that what is happening. Like, if you are having one variable which is being modified at two places, then you probably want to make sure that if this is getting modified at two places, then at a time only P1 or P2, let's suppose multiple processes or multiple threads, then at a time only one process or only one thread should execute, isn't it? So it means you can say that the very first solution, right? The straightforward solution, right? Straight forward solution that comes to the mind is basically, if this is critical section, then only one process at a time, right? So only one process at a time. Is this okay to everyone? Okay. Now, do you think that if I give you some very naive solution, I mean, if we are putting this as a solution, if you say that okay, this is a solution, which means if somehow I can make sure that only one process at a time, which means if this is T1, okay, x equal to x plus 1, this is T2, which is having, let's suppose, x equal to x plus 50 or x equal to x plus 1 or whatever, right? Okay. So if this is T1, this is T2, let's suppose this is T1 and T2. Let's suppose somehow I make sure that whenever T1 is going to enter into this critical section, there I put some code that makes sure that T2 is not there. And similarly, if T2 want to enter, then that makes sure that anyone else is not there. Okay. If I can do it somehow, which means only if given this critical section, if I can make sure that only one process at a time, basically at most, let's suppose I say that in this critical section, if I somehow make sure that at most one process at a time, then is this a good solution? Tell me, is this a good solution if somehow I make sure that at most one process at a time? So here you need to understand that there can be multiple requirements that we need to fulfill. Let me just tell you what do I mean by that. Let me just tell you. See here. Suppose I propose you one solution. Let's suppose your manager says you are working in a company. Your manager says that okay, this critical section x equal to x plus 1 should be executed by at most one process at a time. Can you implement some solution? Okay, can you implement something here such that it is executed at most one by at most one process at a time? Let me know. So which means suppose if I just say that okay, while one, okay, maybe these are the two processes, and I say that okay, see that this is my solution to the critical section. Maybe you tell to your manager that okay, this is my solution to the critical section problem, which means I will put while one, and I'm actually making sure that here at most one process at a time. Actually I'm saying that no process, right? Because while one, it means that it will get stuck in while loop. It will also get stuck in while loop, isn't it? So if I'm saying while one, is this a good solution? Tell me, is this good solution? Is this a good solution? What do you think? The answer is no, right? See, if you propose this solution, most probably you will get fired, okay, from your company. Okay, they will say okay, it is a completely nonsense solution. So I can say this is a horrible solution, in fact, right? This is a horrible solution. In fact, this is a horrible solution. So what you can do to improve the solution? Maybe you first need to modify your requirement, right? What is your requirement? You said that okay, at most one processor. See, at most one process. So let's suppose your manager tell you that okay, I want some solution which have at most one process at a time, and then you propose the solution. Are you wrong anywhere? Aren't you fulfilling this requirement that at most one process at a time? Aren't you fulfill this requirement which says at most one process at a time? You're already fulfilling this requirement. Still this particular solution is a horrible solution. So at least you need to be very particular that what you want. See, this seems to be some fault of manager or you. Tell me. I mean, this is always manager's fault that I know, but still still you tell me your answer. See, if your manager says that okay, at most one process at a time, and you say that okay, hey, hello manager, this is the solution. Now you tell me, aren't you fulfilling the manager requirement? Since you are fulfilling the manager requirement, then tell me, is this a manager problem that he has maybe miscommunicated something, or this is your problem? Most probably this is manager problem. So manager will realize his mistake and he will say that okay, this at most one process at a time is actually called mutual exclusion. Okay, so this is actually called mutual exclusion, right? So basically your manager will say that see, I'm sorry about it, I'm sorry about it, we need mutual exclusion, that is okay. Okay, that is okay, but I need something else also. Okay, some extra things. Okay, some extra conditions to fulfill. And what could be that extra condition? Can you think about it? What could be that extra condition? The extra condition, let's just talk about that extra condition. See, earlier what is happening here, that it is stuck, right? There is no progress, I mean, this is stuck, this is stuck in the while loop, this is stuck in the while loop. So that extra condition that I'm talking about is called progress. So what I'm saying here, let me just tell you on the next page. See, mutual exclusion plus some extra conditions. Now this extra condition is basically called progress. See, tell me, is only mutual exclusion enough? Is this satisfying the mutual exclusion or not? Is this satisfying the mutual exclusion or not? This solution is definitely satisfying the mutual exclusion. Still, this is a horrible solution. That is why we need some extra conditions, which is called progress also, isn't it? Now let me just define you that what is the progress. Okay, progress is saying, okay, in layman terms I'm telling you, okay, what this progress says, it says that there has to be some progress in critical section. Okay, there has to be some progress in critical section, right? Okay, let me know everyone. Shriyank Jaswal, let me know, is this okay to everyone? Aryan, Sonam, Hemant, let me know. Is this okay? That we need some extra condition which is called progress, right? There has to be some progress in the critical section. Now basically this time you have developed two conditions. One is mutual exclusion. Another one is progress. Now in layman terms I'm telling you, this mutual exclusion says that at most one process at a time, at most one process at a time. Okay, this progress says that okay, there has to be some progress, which means it says that at least one process. Okay, one process, if multiple process wants to enter, right, process should get enter. Let me know if this is okay to everyone. Let me just tell you by the example. Okay, suppose that this is I mean, you can say the prime minister's house. Okay, so here is a PM. Okay, let's suppose here is a PM, prime minister, and then let's suppose this is a lobby. Okay, in this lobby there are some sofa. Okay, let's suppose this is some sofa or something like that. Okay, this is a sofa, this is another sofa or something like that. Okay, this is lobby. Now let's suppose multiple people, P1, P2, P3, multiple people wants to meet Prime Minister. Okay. Multiple people wants to meet Prime Minister. Now what will happen if multiple people wants to meet Prime Minister? Then it may so happen this person should go, and let's suppose Prime Minister can meet. Okay, this is just like a critical section. Okay, the Prime Minister can meet at most. Okay, or you can say that only one person at a time. Okay, only one person at a time. Prime Minister can meet one person at a time. Now let's suppose you implement mutual exclusion. What does this mean? It means two people can't go. But tell me, is this mutual exclusion enough? Alone is enough? Is this mutual exclusion alone is enough? No, because maybe let's suppose all of them are just waiting in this lobby. Okay, if all of them are just waiting, this P1 is sitting here, P2 is sitting here, P3 is sitting here, all of them are just waiting in this lobby. Then also the things are not good. So this mutual exclusion again is alone is not enough. So that's why we need some more condition which we are calling progress. Progress is saying that if multiple people wants to get enter, then let at least one of them enter. Okay, mutual exclusion said at most one. Okay, at most one. It says at least one, right? At least one. So which means exactly one, right? Exactly one. This is very sweet spot. Exactly one. Okay, at most one and at least one. This is exactly one. Which means suppose you implement both of them, which means that not two people can't go, and also all of them can't wait, which means exactly one will go. Then isn't it a good thing? Isn't it a good thing that exactly one is going? So yes, I think we have achieved our solution. So basically mutual exclusion and this progress, right? Progress. So mutual exclusion says that at most one, right? At most one means less than or equal to one. It says at least one. There should be some progress. It says that okay, at most one can go. So combinedly both of them say that exactly one, right? Exactly one should go. Now you imagine this scenario. You imagine the scenario again and tell me, do you really need anything else and any other condition, or these two conditions are enough? Which means if let's suppose you are saying that you are implementing mutual exclusion and progress, aren't you making sure that exactly one will go? Yes, you are making sure. So if you are implementing mutual exclusion and progress both, then you can say that only exactly one person will go, right? Exactly one person will go. So you are definitely making sure that exactly one person will go. But is these two enough? These two enough? Or there has to be some more conditions? So let me just tell you that there has to be some more conditions, right? What is that more condition? Okay, there has to be one more condition. See, just imagine a scenario that exactly one is going, that is fine, but P1 is going, and immediately after P1 go, P1 again comes and again go, right? Is this possible? Yes, this is possible. See, according to mutual exclusion and progress, if you are just having this, if you are just having only these two, right, mutual exclusion and progress, then it is definitely possible that P1 can go and re-enter again. If that is the case, then only P1 will be meeting, right, Prime Minister again and again. Okay, only P1 is meeting Prime Minister again and again. So this is definitely not good. You don't want this P2 P3 to wait, right? You don't want this P2 P3 to wait. So in this case, what will happen? You can say that mutual exclusion and progress both are not enough, basically. I mean, needed but not enough. So what else you know? What else you need? You need one condition which says that okay, if P1 is entering, then it should not re-enter immediately. It may re-enter but not immediately, isn't it? So basically you just had a condition which is mutual exclusion. You had a condition which is progress, right? And the third is bounded waiting. Okay, you had a condition mutual exclusion, progress, and third is bounded waiting. Yeah, P1 is scammer. Yeah, if P1 is going again and again, he might be scammer. Yeah. Okay. So mutual exclusion says that at most one should go. It says there should be some progress, which means at least one should go. If multiple people want to go, then at least one should go. Bounded waiting says that it should not re-enter immediately, right? It should not re-enter immediately. So we need one more condition, which is bounded waiting. Now you just assume, okay, now you just assume that all of this is satisfied, which means in this particular case, you have your mutual exclusion, right? You have your mutual exclusion, you have your progress, and assume you also has bounded waiting. Then tell me, can all of them wait in lobby? Can all of them wait in lobby? Can all of them wait in lobby? No. Why? Because of progress. Progress is saying that okay, not all of them. I mean, there has to be some progress. There has to be someone who is meeting PM. Tell me, can two of them go to PM directly? No. Why? Because of mutual exclusion, right? So exactly one will go. Now tell me, can this be scammer? Which means go out and re-enter again and again. Can this happen? Can this happen? Then answer is no. Why? Because of bounded waiting. So P1 will go, but it cannot re-enter immediately. That is why someone else may get chance, right? Maybe P2 will be getting chance, right? It cannot also re-enter immediately. Is this okay to everyone? So little bit you might have understood. Okay, these are in just layman terms. Okay, in just layman terms, I try to make you understand that what is this mutual exclusion, what is this progress, and what is this bounded waiting. So ultimately, there are, you can say, for any critical section problem, there are basically, okay, whatever solution you propose. See, someone says, let's suppose this is you, this is your manager. Now, if let's suppose your manager wants to say, okay, solve this critical section problem, I mean solve this. So manager won't only say that okay, mutual exclusion should be there. He will say that progress should also be there. He will say bounded waiting should also be there, right? Bounded waiting should also be there. So basically this time your manager says that okay, all of them should be there. Now you tell me, will you dare to propose a solution something like this? Is this solution, the solution that we have wrote earlier, is this solution satisfying? Let's suppose this is a two processes, okay? The two processes. Is this solution satisfying mutual exclusion? Yes. This solution satisfies mutual exclusion. But is this satisfying progress? Tell me. Is this satisfying progress? The answer is no. Answer is no. Okay, no. Understood? Let me know if that is okay to everyone. Okay, so basically this time you won't propose the solution. This time you have to really propose something meaningful. So finally you understood that if you really want to solve critical section problem, then mutual exclusion alone is not enough. You have to have progress. You have to have bounded waiting also. So hence this time you will say that see, no, progress alone is not enough. We need three things, right? We need three things. By the way, can you tell me, is this satisfying bounded waiting? The answer is yes, because in deadlock, it is by default satisfied. I mean, bounded waiting says that it should not re-enter immediately. If it is not even entering one time, okay, if it is not even entering one time, so there is no question of making it false. Like, I mean, it is not re-entering immediately, right? So yeah, that is true. It is not re-entering immediately because it is not even entering one time. So anyway, bounded waiting by default satisfied. Okay, let's not worry about it. Okay. Okay. So I hope you understood that we need to solve any critical section problem. We need how much? We need three requirements basically. We need to satisfy, right? What are those three things? Mutual exclusion, progress, and bounded waiting. Understood? So these are called requirements of critical section. Okay. So see here that what will I do in before the critical section, I will write some entry section. Okay, this entry section and exit section I will write, and this is called the solution of critical section. So basically this should satisfy these three things, right? The critical section solution. So these are the three things that it should satisfy. Allow at most one, mutual exclusion, progress allow at least one, right? Bounded waiting, don't allow to re-enter immediately. If others are waiting, okay, if others are waiting, then don't allow to re-enter immediately. If others are not waiting, then that's fine, obviously, right? I mean, that is fine if others are not waiting. Okay, so now let's just see that in real life how we can implement this mutual exclusion. Okay, in real life how we can implement this mutual exclusion. So how do we do it? Let's just see it. So basically, as a user, we can write some code. I mean, you can write some code before the critical section. You can say, okay, let me write some code. Maybe we can ask help from operating system. Maybe we can ask help from hardware itself. So these are the three type of solutions, right? One is we write code by ourselves. Another one is we ask help from operating system. Another one is we ask help from hardware. Is this okay to everyone that what I'm talking about? Let me know. Okay, so let's just have the very first solution, which is we are writing the code by ourselves, right? So let's just write a code by ourselves, which means let's suppose there's a shared variable. Maybe the value could be anything. Okay, so this is a shared variable, and I let's suppose this is a critical section, and here there might be some process which is modifying this value, right? There might be some process. Let's suppose this p1 is modifying, p2 is modifying here. Now I want to write some solution of this critical section problem. Let's not write x again and again. So basically I want to write the solution of this critical section problem such that it satisfy all of the requirements that I have, right? All of the requirements that I have. So suppose here this is the critical section, here this is the critical section. Now before this I want to write something, and maybe after this also, which is called entry and exit. Before this I want to write something, after this also maybe, right? So let's just see what we can write. Let's suppose there's a variable interested, okay, which is just shared variable. Let's suppose this interested, okay, initially let's suppose it is a 0. It is a shared variable. Now I will say, maybe I can go to the next page. I can say while interested is 1. Okay, then I'm here only. Okay, if interested is 1, then I'm here only. The moment interested is 0, I will go inside and I will write interested. I will set it 1, right? Interested equal to 1. And let's suppose this is my solution. Okay, this is the critical section. So basically what I'm saying, that I'm writing the solution of critical section problem. This is my first attempt. Okay, this is my first attempt. So here what I'm saying, that let's just have a while loop here. If it is 1, then it will stuck in the loop. Otherwise, if it is 0, then it will go inside. Or maybe I can write something like this in short form. Maybe I can write something like this. If it is 1, it will stuck in the loop. Otherwise, it will go inside. Interested equal to 1. Okay, let's suppose. And this is the critical section. Tell me, is this a good solution? Is this a good solution? Can you tell me? Let's suppose this is a solution for P1 and P2 both. Is this satisfying all of the conditions that we have? Let's just check. Okay, this is P1, this is P2. Is this satisfying all of the conditions that we have? Let me know. Is this satisfying mutual exclusion? Let's just check quickly. Mutual exclusion says that, okay, let's suppose interested is initially 0. Mutual exclusion says that, okay, only one of them should be going. If interested is 0, then it will go, it's because it is 0, it is false, it will go inside, and interested, it will make it 1. And then it will go to the critical section, isn't it? So now this P1 is in the critical section. At the same time, see if P2 can come. Can P2 come? See, P2 can't come because now the interested is actually 1, right? Now the interested is 1. Since it is setting the interested 1, right? It is setting the interested 1. So that's why P2 will get stuck here. So P2 can't come whenever P1 is in the critical section, right? But here is a catch. It might also so happen that both of them, see, P1 execute this and then get preempted before setting. Okay, before setting get preempted here at this point in time only. Which means P1 get preempted at this point in time. Now P2 can execute this. It will say, okay, interested is false. Let me get enter, and P2 is also here. See, P1 is also here and P2 is also here. Is this possible? Since this is possible, that is why you can say that both of them will set this interested equal to 1 simultaneously. Both of them can access the critical section. So the very first naive solution that is coming into my mind is basically a bad solution because it is not satisfying not satisfying mutual exclusion itself. Right? Understood how? Because see, always the preemption can happen anywhere. So see, many of the students get confused that where to preempt, where to not preempt. So you can just think that in terms of like this, that for the preemption, just think that, okay, before or after while loop. This is basically this is the sensitive areas. So just after, immediately after while loop, okay, just try to preempt immediately after while loop. And here if you preempt, then P1 will be here, and if you check, then P2 can also execute, right? P2 can be in the critical section, P1 can also be in the critical section at the same time, right? So hence you can say that it does not satisfy mutual exclusion. So whatever you have just proposed, right? I mean, the solution that you have just proposed, it does not really satisfy the mutual exclusion. So it's not a good solution. I mean, we can check other conditions also, but at least it doesn't satisfy the mutual exclusion at least, right? So you can say this particular, whatever you have just proposed does not satisfy mutual exclusion. Okay. So it is not satisfying mutual exclusion. Let me know, is this okay to everyone? Okay, why it is not satisfying? Because both of the process can get entered into the critical section. So this is one reason. That is why it is basically not satisfying the mutual exclusion. Hence, it is not a good solution. So you can say okay, we can talk about the progress and these things. Can you check whether the progress is satisfied or not? What does the progress says? Progress says that at least one should go, right? At least one should go. So is this possible that let's suppose that both the processes wants to go. So are you allowing at least one? If interested is initially 0, okay, interested is initially 0. Are you allowing at least one? Yes, right? You are definitely allowing at least one. So since you are allowing at least one, that is why you will say equal to 0. You will say that, yeah, we are definitely allowing, maybe we can even allow both of them, right? So we are definitely allowing at least one. So hence progress is satisfied. What about bounded waiting? Bounded waiting is very interesting to check. I will tell you the systematic way to check. Don't worry. But bounded waiting, here I'm just telling you. Okay, like I will have a slide to tell you that what is the systematic way to check all of this. Okay, we will just see in a just while. We will just see that what is the systematic way to check. Here I'm just telling you upfront. See, we will have a slide, a systematic way to check. Okay, don't worry about it. See here, if you want to check whether the bounded waiting is satisfied or not, what you need to do, you just see if the bounded waiting says that P1 is in critical section and P2 is waiting. P2 is in waiting area. Can you tell me what is the waiting area here? This is a waiting area, right? In that case, P1 should not come out and should not enter again. Okay. So if P1 is in critical section, it means the interested must be 1. I mean, it must have made it 1. And now P2 is in the waiting area, right? So P2 is here, P1 is here, interested is 1. Okay, this is a setup. You can say this is setup to check bounded waiting. So is the initial setup is clear to everyone? We will check bounded waiting in a while, but initial setup, as an initial setup, should be one of the process in the critical section, another process should be in the waiting area, and then you check, can you go out, go in again? Tell me, can you go out and go in again? Since interested is 1, can you go in again? Tell me. Let me know. Can you go again? No, right? Okay, sorry. Here at the last, interested. While you are leaving, let's just put, okay. Let's just put interested at 0. While you are leaving, let's just put interested at 0. Okay. Now you tell me. Here at the both the places, interested will be 0 while you are leaving, right? Now you tell me that if it is going out, okay, if we are here, he is here, and if you are going out, then interested will be 0. Can you enter again? Can you enter again while he is waiting? See, if you check here that P1 is in the critical section, it means the interested is 1, right? Interested will be 1, and P2 is waiting. That is fine. Now, since interested is 0 now, then it can go out and can re-enter immediately, right? Assume that P2 is not even scheduled by this time, right? So basically you can say it can re-enter immediately. Since it can re-enter, that's why bounded waiting is also not satisfied here. Okay, bounded waiting is also not satisfied. Understood? Because it can re-enter immediately. Since it can re-enter immediately, that is why bounded waiting is not satisfied. So in this particular solution, it is not satisfying mutual exclusion, it is satisfying progress, and it is not satisfying bounded waiting, right? So it is not satisfying mutual exclusion, satisfying progress, and not satisfying bounded waiting. Let me know it is okay to everyone or not. Okay. So see, don't worry about this solution, and don't worry how to check. I mean, because we will see very clearly how to check. But this was just our first attempt. You don't need to remember this attempt. You don't need to remember that, okay, whether mutual exclusion satisfied or not, or and so on. Okay. Let's just see that how to systematically have a way to check these 3 things, right? Mutual exclusion, progress, and bounded wait. Because this is very important to understand. Then only you will be able to solve the questions. So the very first thing is mutual exclusion, and then progress and bounded wait, right? So these things, let's just see how to check. Let me know if there is any issue till this point. Let me know. Okay, I hope you are getting right. Okay, great. So now we will see that how to check all of this, right? Which is mutual exclusion, which is bounded wait, which is progress. Systematically we will see. See, this particular slide that I am talking about, I have taken from University of Otaha. Okay, so this particular slide is basically from Standard University only, which is University of Otaha. Okay, this particular slide from Standard University only. So let's just see that what this University of Otaha is saying. Okay, so if you want to check mutual exclusion, then what you need to do, you have one process in the critical section and another process tied to enter. See, they are saying if you want to check mutual exclusion, then let's suppose this is critical section, right? Okay, one process in the critical section, and you check if another process wants to enter. Can this can enter? If this can enter, then mutual exclusion not satisfied. Otherwise, you just check both of these conditions. Okay, like if you want to check mutual exclusion, then these are the 2 conditions. Okay, 2 conditions you need to check. One is that one process in the critical section, another process try to enter, and show that second process will block in entry code. Okay. Second condition is saying two or more processes are in the entry code. Okay, two or more processes are already in the entry code. Okay, maybe P1, P2, two or more processes are already in the entry code, and then show that at most one will enter in the critical section. Which means they are saying these are the two conditions that you need to check for the mutual exclusion, which is if one is already in the critical section, then check if P2 is coming, then it should get blocked, right? If two or more are coming, then only one should go, only one should pass. Okay. So if both of these conditions are satisfied, then mutual exclusion is basically satisfied. We will see that how to have the example, but for now let's just see that what they are saying. This progress condition is basically says that no process in the critical section and P1 arrives, P1 should get enter. So these are also having two conditions. It is saying if no process in the critical section, if P1 comes, then P1 should get enter. And if multiple processes, okay, if multiple processes at the same time wants to come, okay, if multiple processes at the same time wants to come, then at least one should get enter. This is what progress says. Okay. Now the third thing is that, which is bounded waiting. Bounded waiting is basically defined like this, that they are saying one process in the critical section, another process is waiting to enter. Okay, see this initial setup is very important, that one process in the critical section and another process is waiting to enter, which means for the bounded waiting, you say that okay, one is already in the critical section, P1, another is waiting, okay, P2 is waiting. Then it should not be the case that P1 come out and enter again. It should not be the case. It should not re-enter immediately. Otherwise, it can re-enter basically immediately again and again. So that if first process exits the critical section and attempts to re-enter, so that it does not get re-enter or enter finite times. So what does this mean? That either it doesn't get re-enter immediately, okay, it comes out, then it should not re-enter immediately. If you are allowing, let's suppose by chance you are allowing, then you should not allow it again and again basically, okay. Maybe at most 2 times, 3 times, 5 times, maybe finite times you can allow. Okay, don't worry that finite times, what is this finite times, it will get clear with the more examples. So let's just see the examples here. Okay, so let me quickly revise that how to check for mutual exclusion. You will say that okay, if one is in the critical section, another wants to enter, it should get blocked. If both of them are coming, then only at most one should go. Okay, at most one should go. Progress says that okay, if one wants to come, it should come. If multiple wants to come, at least one should come. It is very easy, right? It is very easy because there should be some progress in the critical section. Bounded waiting is also very easy. The initial setup is just important here. Okay, don't worry. Let's just see the attempt 2, and we will see whether this attempt satisfies all of these conditions or not. So this is our another attempt to solve critical section problem. Why I am calling it another attempt? Can anyone tell me? Because the first attempt got failed. Because the first attempt hasn't satisfied all of the conditions, all of the requirements of critical section solution, right? Mutual exclusion is one requirement, progress is another requirement, and bounded waiting is another requirement. Now let's just see if this particular solution satisfies all of this or not. Okay, maybe we can check it. Let's suppose initially turn is 1. Okay, it may be 0, it may be 1. Actually, it doesn't matter for this particular problem because it is symmetric. But if it is not given, then you should be checking with both of the values. Okay, with 1 also and with 0 also. Okay, let's just assume initially it is 1. Tell me, is mutual exclusion is satisfied? If turn is 1, turn is not equal to 0, it is good. Then it will get entered into the critical section, right? Tell me, can both of them get into the critical section? If turn is initially 1, so I will say okay, it is not 0, so that's why it is good. So okay, turn is not, sorry, it is not good. So turn is 1. It means turn is not equal to 0. It means it will satisfy. It means it is basically waiting here. P1 is waiting here, and then or maybe I can call it P0 is waiting here. P0 is waiting here. Maybe this process is waiting here, and then this process will say that okay, turn not equal to 1. This is false, right? Since this is false, it will get enter. So if both the process wants to get enter, then only one of them will get enter because of the obvious thing that turn is a shared variable and it can take either 1 or 0 at a time, right? So if it is 1, then it is its turn. If it is 0, then it's its turn. But let's just check systematically. What is the systematic way to check mutual exclusion? One process in the critical section, another wants to enter. Tell me, if you have one process in the critical section, and now at that time, if another wants to enter, which means turn is 1. Now if this wants to enter, can it get enter? No, right? Okay, so it can't enter. So basically, the first condition of mutual exclusion satisfied. Let's just say another condition. Two or more process wants to enter simultaneously, then at most one. Two or more process wants to enter simultaneously. If both wants to enter simultaneously, then in that case, let's suppose it is not in the critical section, and both of them wants to enter simultaneously. Then in that case, tell me what will happen. If both of them wants to enter, then since turn is a shared variable, it is either 0 or 1, right? So one of them will get blocked. It is not the case that both of them will go. So hence mutual exclusion is satisfied because I have checked both the conditions. What are both the conditions? One of the process in the critical section, maybe you can keep this P1 is in the critical section. One of the process in the critical section, another process wants to come, can't come. Both of them wants to come simultaneously, only one will get, right? Okay. Let's just check progress. Progress is also very easy. It says that there should be some progress. It just check that okay, if one process wants to enter, then it should get enter. And if two process wants to enter simultaneously, then at least one enter, right? So tell me, if two process wants to enter simultaneously, then should at least one enter? Okay, just tell me here. If two processes wants to enter simultaneously, will at least one will enter? Yes, if turn is 1, then this will enter, right? If turn is 1, then this will enter. But this is not enough. Okay, see, for the progress, it is not enough to check that okay, if two process wants to enter simultaneously, then one will get enter. You have to check one more thing, which is that if let's suppose this P1 is not interested, okay, let's suppose P1 is not interested to come in the critical section. P1 is executing somewhere here outside critical section, or maybe somewhere long before the critical section. Basically, it is not currently interested. Currently P0 is interested, but turn is 1. Okay, only one of them wants to come. Can it come? Can it come? Tell me. It since it can't come. See, for the progress, you have to check both the things. If one wants to come, it should be coming. If multiple wants to come, then at least one, right? See, it is having two conditions. If P1 arrives, no process in critical section, P1 arrives, P1 should get enter, right? Two or more process wants to come, then at least one enter. So two or more process wants to come, then at least one enter is satisfied. But if just one wants to come, let's suppose this wants to come, then it can't get enter because turn is 1 here, right? Hence, progress is not satisfied. What about bounded waiting? It says that you keep one of the process, right? It doesn't matter which one because it seems like a symmetry. So maybe you keep this here. Okay. See, the initial setup of the bounded waiting should be clear to everyone. What is the initial setup? You keep one of the process in the critical section. You keep one of the process in the critical section, and another process is in the waiting area, which means P1 is or P0 is waiting here because turn is 1 initially, right? Now tell me, can it go out and come in again? See, no, because turn is 0. Since turn is 0, that's why it can go out but can't come in again because turn is now 0. Actually, it is strict alternation because if it go out, turn is 0, and then it should get enter. It can't get enter because turn is 0 and 0 is not equal to 1. It is true basically, so it will get stuck. See, before I tell you that bounded waiting is satisfied or not, you should understand that this is initial setup of bounded waiting. Is this initial setup is clear? Since the initial setup is this, that okay, you wait one of the process in the critical section, another you have one of the process in the critical section, another process is waiting to get into the critical section in the waiting area, then can it go out and can enter again? Then answer is no, because that it is basically the strict alternation, right? So this is the initial setup and bounded waiting is satisfied here. So you can say that in this attempt 2 mutual exclusion satisfied, right? Because only one of them will go. Progress not satisfied because only just let's suppose P0 wants to go, it can't get enter. And the third thing is that bounded waiting is satisfied. Is this okay to everyone? Why bounded waiting is satisfied? Because it can't get enter again. That is why, right? Okay. Okay. Great. Cool. I hope you understood this, right? You understood this a little bit. See, actually, bounded waiting not only says that it can't get re-enter. It may get re-enter, maybe, but only finite number of times. But this is very rare that they will ask that, okay, these kind of questions. So I'm just saying that it should not get re-enter. If it is getting re-enter, then you should be checking, is it finite times getting re-enter or again and again? Since it can re-enter again and again, that's why bounded waiting is not satisfied. Sorry, it can't get re-entered. That's why bounded waiting is satisfied, right? Okay. Okay. So Aryan is saying in the first example, Warner waiting, I think it was satisfied. So we will later on look that particular example. Okay, the attempt one you are saying, right? Attempt one you are saying that bounded waiting is satisfied. We will later on look that. Okay, let's just keep on continuing in the flow. So here in this the progress is not satisfied. Why? Because one of the process wants to come, it can't get re-enter. See, do you have deadlock here? I mean, maybe currently you might not be familiar about the deadlock, but those who are familiar about the deadlock, tell me, do you have deadlock here? Yes, even after re-enter, sometimes very rarely they might ask the question that I mean, they might set up such a case that it is only re-entering finite times. If it is re-entering finite times, then it is okay. The bounded waiting is satisfied actually. Okay, don't worry, they will not ask you such tricky question, but if they ask you, then I'm telling you this. Okay, if they ask you, you tell me this, that do you have deadlock here? No, right? I mean, either this, it is strict alternation, right? So strict alternation means that first, let's suppose P1 is going, then P0 will go, then P1 is going, then P0 will go. There is no deadlock. No, there is no deadlock here. You just tell me that is progress satisfied? It is not satisfied. So see, some people think that progress and no deadlock is same, which means misconception. This is misconception. Some people think that if there is no deadlock, then there will be a progress, or there is a deadlock. Okay, I mean, that is actually true, but yeah. So if there's a deadlock, then there will be no progress. I will tell you why. But if there is no deadlock, then there will always be the progress. This is false. Okay, this is false. See, there is no deadlock here. Still, the progress is not satisfied. Why? Why that is the case? Can anyone tell me? Because progress is basically having two conditions. If you remember, that it is saying no process in the critical section, P1 arrives, P1 should get enter. So if progress is not satisfied, then it may be because one of the reason. Okay, see here, you tell me this progress is satisfied or not. Progress is not satisfied, right? Now you tell me, out of these two region, which one is basically making the no progress? See, tell me, is this satisfied? No, right? Is this satisfied? Two or more process in the entry code, at least one. Yes, this is satisfied. Since this is not satisfied, so progress is not there. So if there is no progress, then it is not only because of the deadlock. See, this particular thing is same as deadlock. This condition is same as deadlock. Okay. Which means if two or more processes are in the entry code, so that at least one will get enter, right? This is same as deadlock. So you can say the progress is not only just deadlock, right? Progress basically means no deadlock and one more condition. What is that? If only one process, then it should get enter. Something like this. Okay. Okay. So don't worry, you will get to understand more. Okay. So here, what I'm saying, that mutual exclusion is satisfied, progress not satisfied, bounded waiting satisfied. Let's just see more examples, and then you will get to understand more. See, let's just have another attempt where let's just like what I want to ultimately do. I ultimately want to do mutual exclusion to be satisfied. I ultimately wanted to do bounded waiting to be satisfied. I ultimately want to do the progress to be satisfied. Let's just see if this particular solution satisfies all of them. Okay. Okay. So here you tell me that is this satisfying mutual exclusion? How to check for that? Can anyone tell me how to check for the mutual exclusion? You just check, or maybe you can check for the progress quickly. Okay, first you can check for the progress and bounded waiting. Whatever you want to check, it is okay. Okay, so let's just first check maybe for the progress, or maybe let's just check for the mutual exclusion itself. So what does mutual exclusion say? If both of the process wants to enter simultaneously, then at most one. So see, want equal initially these are false. So if both of the process wants to enter, then it will be true. It will be true. Then it will get stuck. It will get stuck. So there's a deadlock that I can see, right? That I can definitely see. But tell me, mutual exclusion satisfied or not? Mutual exclusion is at least satisfied because not two processes are not getting enter simultaneously, right? So mutual exclusion have two conditions. One of them is satisfying, that okay, both process try simultaneously, then only at most one should enter. If one of them is in critical section and another wants to try, so if this is in the critical section, then can you tell me what is the 1 1 0? 1 0 should be true. If another wants to try, then can it get enter? Once one is true, so this is true, then 1 0 is true. No, it can't get enter, right? So if one of them is in the critical section, then another wants to try, it can't get re-enter. So hence the mutual exclusion is satisfied, right? Because if both of them wants to enter, then at most one is, yes, is entering at a time, right? So maybe why? Because if either you will say that it will enter or it will enter. Why? Because if both of them are saying true, then both of them won't enter. If one of them is only executed true, then by this time only, then it can get enter because it is initially false, right? If it is here, it is not setting the value to be true, then one of them can get enter. So basically mutual exclusion is satisfied. Now tell me, what about the progress? Progress says if one process wants to enter, let's suppose wants 0 want to enter, can it get enter 0? This is false, it can get enter. So one of them wants to enter, I think it can get enter. If two of them wants to enter, then here if two of them wants to enter, it may be possible that both of them are stuck, right? So hence progress is not satisfied. See, here the progress is not satisfied because of the deadlock, right? Earlier progress was not satisfied because of the, not because of the deadlock, because of something else. See, earlier the progress was not satisfying because if one of the process wants to enter, then it was basically getting stuck because it is strict alternation. Okay, it is strict alternation. So if one of them wants to get enter, one of them, let's suppose this process 0 wants to get enter into the critical section, it was not able to enter, right? Okay, let me know if that is okay to everyone. So here the progress is not satisfied. Now let's just see the bounded waiting. It is very easy. It is very easy to check. How? You just check whether in this critical section, one of them you put in the critical section, another one you put in the waiting area here. Okay, P1 is here, P0 is in the critical section. Which means if P0 in the critical section, it means 1 0 must be true, right? If P1 is here, it means it is true, and 1 is also true because it has executed this. Both of them are true. Now tell me, can it go out? Which means it will be false. And then can it go again? Enter again, it will be true. And then since once one is true, it can't get enter again, right? It can't get enter again. So it can't go out and can get enter again. Hence the bounded waiting is satisfied. Let me know. So mutual exclusion satisfied, bounded waiting satisfied, but progress is not satisfied. So we have, I think this was our third attempt, and we have seen in this third attempt also we were failed, right? We were failed. But why we are even checking these failed attempts? So that you really get to understand what is the real solution, right? I mean, in the questions also they will ask such things. So here bounded waiting is satisfied, right? Great. See, let me just tell you one of the common mistake that people do. Okay, one of the popular mistake that people do. Let me just tell you. So one of the popular mistake. what they think, they do not put, okay, they do not put other process in the waiting area. Okay, they do not put other process here. They will say, so initially these values are like this. See here, they will say, just a second, let me just copy this so that it is on the same page. Okay, so they will say that see, this is wants to is false, and then if it is in the critical section, then this particular will be true, and then it will be false, and then this will be 0 or 0 again, which means it is again true false true false. Ultimately it is true, right? Ultimately it is true, and then let's suppose this is false only, right? This is false only. They will say that since this is false, it can go and re-enter. It can go and re-enter, right? They will say it can go and re-enter. They will not put this in the waiting area. That is a major problem. Okay, they will not put this in the waiting area. And since they do not put this in the waiting area, hence they think that bounded waiting is satisfied. Sorry, not satisfied. So they will think, many of the people will say that bounded waiting is basically not satisfied here. This is the common mistake. Okay, they will think that bounded waiting is not satisfied. Why? Because the initial values are like this. How many of you do the same mistake? Tell me. How many of you do the same mistake? See, many people do this mistake, not just one or two. I have seen many aspirants do this mistake. They say that okay, it can go and come again, can go and come again. They do not put the other process in the waiting area. How many of you do the same mistake? Okay, so they do not put other process here. So you will say here in this particular scenario, bounded waiting, I mean, many people say not bounded waiting not satisfied. This is wrong. Okay, this is wrong. See, Aryan now got his mistake, I think, right? Aryan is also saying that he did in the very first example, right? Okay. Let me know if you have understood things clearly. They basically say that they do not put other process here, and they say okay, it can go and re-enter. The first thing is here that initial setup should be clear to everyone. See, what is the initial setup? This is the initial setup. See here, what it is written. In the bounded waiting, one process in the critical section, another in the waiting area waiting to enter. Okay, this is the initial condition, initial setup. Okay, another is waiting to enter. This is the initial setup, and then you need to show if the process exits the critical section, attempt to re-enter, show that it does not get re-enter or enter finite times. Okay, great. Now I think this is okay to everyone. This is a popular mistake that people do. Okay. Now let's just see the formal definitions. Okay, formal definitions or the textbook definitions of mutual exclusion, progress, and bounded wait. So basically we have seen in the layman terms what does this mean. Okay, in the layman terms what does it mean, we have seen, but let's just see the formal definitions also, right? So see, I have taken this from Galvin. So what they're saying, I mean, you don't need to remember or something, I'm just telling you quickly. Okay, they're saying if process Pi is executing in its critical section, then no other process can be executed in their critical section, which means the same thing, right? I mean, we have also understood the same thing. In the progress, what we have understood, that there should be progress, right? There should be progress. So basically we have understood that okay, if one process wants to enter, then it should get enter. Multiple process wants to get enter, then at least one should get enter, right? So we have understood the progress in two ways, right? I mean, in two points. If one process wants to get enter, it should get enter. If multiple process, more than one, then at least one should get enter, right? We have understood in 2 points. Let's just see what the formal definition says. If no process is executing in its critical section and some process wish to enter in the critical section, see, this is just one, right? I mean, the very first condition, if no process executing and one process wish to enter, then only those processes that are not executing in the remainder section can participate in deciding which process will get entered in the critical section next. And this selection cannot be postponed indefinitely. So basically, they are saying that if one process wants to get entered in the critical section, then only the process who are basically who may come. I mean, who are in their entry section, right? I mean, they are not in the remainder section, right? I mean, they are not after the critical section. Then only those process executing in their remainder section are not executing in the remainder section can participate. So basically it is saying if multiple processes wants to get enter, then at least one can enter because the selection cannot be postponed indefinitely. I mean, don't worry about this formal definition, but I'm just telling you that yeah, if you want you can read it and you can definitely relate to these formal definitions to this University of Otaha. Okay, so you can definitely relate the Galvin definition and this University of Otaha definitions. So this and this you can definitely relate if you want to. Otherwise, there is no need. Okay. Otherwise, there is no need. The third thing is bounded waiting. It says there exists a bound or limit on the number of times that the process are allowed to enter in their critical section after a process has made a request to enter in the critical section before the request is granted. So basically, they are saying there has to be a bound that the process. Let's suppose this is P1. They are saying on the limit of time the process are allowed to enter in the critical section. Basically, if you are going, then if you can't go again and again, right? This is what they are saying. There should be limit. Okay. In the after process has, and other thing. Let's suppose P2 is just waiting. Okay, P2 is just waiting. It should not happen. Okay. If other process after a request has been made to enter in the critical section. Okay. Anyway, like these definitions and those definitions are exactly same. Okay, these definitions exactly same. Okay, now let's just see some gate questions. Okay, let's just see. Now see, tell me, are you little bit familiar to check how to check mutual exclusion, how to check progress, and how to check bounded waiting? For progress, just see one wants to enter, can it get enter? Multiple wants to enter, can at least one get enter? For bounded waiting, the initial setup I hope is clear that one is in the critical section, right? Another one is waiting. It can't go and re-enter, right? That's the initial setup of bounded waiting, right? Mutual exclusion is also very easy. Let's just see that how to check for all of this. Here, let's just they are just asking mutual exclusion and progress, right? Mutual exclusion and progress. Okay. Now you tell me, is mutual exclusion is satisfied here? See, I think they have not given the initial values of S1 and S2 shared variable, okay, are randomly assigned. They are saying they're randomly assigned. You can take any value, doesn't matter. Okay, you can take any value. I mean, either this condition is true basically or this condition is true, because either both of them are equal or both of them are not equal. So if this condition is true, let's suppose that both process wants to get enter, then only one of them will be true, right? So you can't get let enter both of them. Okay, so mutual exclusion have two conditions. If both wants to get enter, then you can't get let both of them enter. Another thing is that if one of them is here, which means if S1 is actually not equal to X2, if one of them is here, then only one of them is here, then can it get enter? No, because S1 is actually not entered into, S1 and S2 are not actually equal. So mutual exclusion is satisfied. What about the progress? What about progress? Progress says if both, let's suppose one by one, if one wants to enter, let's suppose S1 and S2 are both really equal. If one wants to enter, can it get enter? Can it really get enter? If one wants to get enter, then can it really get enter? You forget about 2. You just tell me if one wants to get enter. Can it really get enter? Okay. The answer is no, right? Answer is no. Either this will not get enter. Either this will go. If you are saying that okay, this either this is true or this is true, right? So because of symmetricity, you don't need to check both of them. That is okay. But either this is true or this is true. So definitely you can say the progress is not satisfied. Let me ask you about the bounded waiting. Okay. Let me ask you about the bounded waiting. This is interesting question here. I will tell you why it is interesting. Tell me, is bounded waiting satisfied? Is bounded waiting satisfied? What does bounded waiting says? It says that okay, let's have the initial setup. Let's have one of the processes here, which means S1 and S2 must not be equal, right? So one of the processes here, P2 is here and P1 is here. Now both of them will be equal. After this, both of them will be equal. Now tell me, can it go out and re-enter again? Can it go out and re-enter again? See, S1 and S2 are equal, so it can't re-enter, right? It can't re-enter. So bounded waiting is satisfied, that's okay. But actually, this code, they have not even asked for the bounded waiting and there's a reason behind it. Can you think about the reason? In the options also, they have not asked about the bounded waiting. What is the reason behind it? What is the reason behind it? See, for the bounded waiting, it should not be indefinitely enter, right? It should not go out and can go enter again and again, something like this. For the bounded waiting, it should not be indefinitely enter. Is this okay to everyone? Since it is not since here interestingly, if that is the only code given to you, okay, if that is the only code given to you, then tell me, can you even re-enter? Is there a while one or something? Is there a while one which is allowing you to re-enter? You are executing again and again? No, right? I mean, generally they will, if they're asking about the bounded waiting, generally they will give the while one. See here in the next question, they are asking about the bounded waiting, right? And then they are saying while true. So if they ask about the bounded waiting, then generally they will give the bounded. They will give the while one. Is this okay to everyone? How many of you knew it? How many of you knew it? That for the bounded waiting, they should give the while one, because I need to check whether it can re-enter or not. Otherwise, bounded waiting is definitely, I mean, in any way satisfied, basically, right? Okay. Now, what is the answer here? Mutual exclusion is satisfied, but progress is not satisfied, because it seems like that one of the process can't get enter. So A is the answer, right? Mutual exclusion, but not progress. So answer is A. Okay. EG and nice question. EG and nice question. So this was one of the PYQ that we have solved. Okay. So now let's just solve another PYQ here, which has been asking gate 2007. So what I did, this particular code I have written, I think, on the next slide. So maybe just to make it little clear. Okay, there's a while one. On top of that, but I'm not writing it. Okay, it can be, I mean, by default understood that there's a while one. Okay, on top of it. So now let's just check if mutual exclusion is satisfied or not. So initially, what is the value of wants 1 and wants 2? Code. Okay, anyway, they are setting wants 1 to true here. Okay, doesn't matter what is the initial value, but yeah, they are setting it to true here. They are setting wants 2 to true here. Okay, so let's just have these values. Wants 1 equal to true here, wants 2 equal to true, right? Now tell me, is mutual exclusion satisfied? See, if both of them wants to enter, then can you allow both of them? Maybe let's just check. See, if this is even before the this for loop, before this while loop, it should be true. Now if both are true, both of them will get stuck, right? That's okay for the mutual exclusion at least. But progress is definitely not satisfied. But yeah, that's okay for the mutual exclusion at least. And the second condition for the mutual exclusion is that one of the processes here, okay, maybe this process is here, P1, and P2 wants to enter. Now it means that this is true and P2 wants to enter, this is really true, and then wants 1 is true, right? Okay. Yeah, so basically this is if this wants to enter, since wants 1 is true, it will get stuck, so it can't get enter. So mutual exclusion is satisfied, right? Mutual exclusion is satisfied. So you can say mutual exclusion is satisfied. Okay, wants should be initialized to false. Yeah, they are initialized to false, because then only you can check these conditions, right? Because if it is in the critical section, if it is waiting, then it means I mean, it can get entered in the critical section only when, let's suppose initially both are true, then none of them can ever enter into the critical section, right? Okay, anyway, so both are initialized to be false. It is given in the question that both are initialized to be false. Okay, so mutual exclusion satisfied. What about progress? Progress says if one of them wants to enter, because of the symmetricity, you can check anyone. If one of them wants to enter, can it get enter? True. And then wants to is true. No, it is not true. So it will get enter, right? If one of them wants to enter, it can get enter. But if both of them wants to enter, so it will get stuck, right? So that's why progress is not satisfied. Progress is not satisfied. What about bounded waiting? Bounded waiting initial setup is that one of the processes here, maybe P1, another one is here. To have this, you must have wants one to be true and wants to must be false, and then then only can get enter. But since it is here also, so that's why you can say wants to is also true, right? Both of them are true. Now tell me, can it go out? Which means wants one is false. Okay, wants one is false. Can it go out? And wants one is again true anyway. Can it go out? Can get re-enter? No, right? It will basically catch it. So you can say this is the initial setup, right? Initial setup means P1 is here in the critical section, P2 is waiting. This is the initial setup. And then can it go out and re-enter? The answer is no. That's why bounded waiting is satisfied, right? Okay. So mutual exclusion is there, progress is not there, and bounded waiting is satisfied. What they're asking? True. It does not ensure mutual exclusion. No, it ensure. It does not ensure bounded waiting. No, it ensure. It requires the process enter in the critical section in the strict alternation. Okay, we will see that it does not prevent the deadlock but ensure the mutual exclusion. Yeah, it does not prevent the deadlock and it ensure the mutual exclusion. Does it require the strict alternation? Can P1, let's suppose P2 is not even interested, can P1 go and come and again? Yes, right? If P2 wants to is false, right? So it does not require a strict alternation basically. So D is the correct answer here. Let me know if this is completely understood to you guys. Okay. So this was one question. This is another question that we have solved. Now, mutual exclusion, second condition says that one of them in the critical section, another one wants to get enter. Okay, another one wants to get enter. You do not check re-enter or anything. Okay, in the mutual exclusion, you do not need to check re-enter and anything. Okay. So D is the correct choice here, right? Now let's just see this question which has been asked in 1988 basically. P0 and P sharing the variables. The program below is the process whose being other one. Okay. Determine the solution is correct if it is incorrect. Okay, what you can do for this particular program, I have written it here basically, okay, as P0 and P1 separately. Okay, I've written it here. You can check mutual exclusion, you can check bounded waiting, you can check progress. Okay, just do it as an homework. Okay, you just check all of this. Okay, just check all of this and comment your answer that what you are getting. Okay, for this 1988 question, I have written this as separately. Just check all of this. Okay, and let me know what is the answer you are getting. Cool. Now you see this, two processes X and Y needs to access the critical section. Consider the following synchronization construct used by both the processes. So process X and process Y, right? Now what they're saying that maybe I have it not, okay, I don't have in the next page. Maybe I can just copy it. So they're asking mutual exclusion, deadlock, and these things, right? Let's just see on the next page. Okay, both the variables which are var p and var q, they are saying both are initialized to false. What they're asking is mutual exclusion and progress basically, or the deadlock. Let's just see. So see here, this is while true, that is fine. Now they're saying both of them are initially false, right? So where p is false or where q is false. Okay, let's just check mutual exclusion. Tell me if both the process wants to get enter. I think it is very standard case that they can get stuck, right? So deadlock is definitely there. Now tell me, can both of them in the same time, can both of them in the critical section? No, right? If this is true, then both of them, for both of them to be in the critical section, both has to be true, right? At the same time itself, right? So since both are, it is not possible. It seems not possible, right? Tell me, Now suppose one of them is here, one of them is here. Another one is basically where it will be. So here there is no waiting area as such. I mean, there is no infinite loop. I mean, the waiting area itself is this one, right? So let's suppose one of them is here, which means where p is true, and suppose that uh, this is true and where q is false, right? Where q is false. If one of them is here, then it is possible that it can get also can also enter. Is this possible? Where q will be true, since where p is true, right? I think it can enter. So it prevents the deadlock. Okay, I think there is some mistake that we are doing. So let's just check the deadlock. So maybe we can check the deadlock first. Can you check for the deadlock first? See here, this is the interesting code. Here you do not have while, I mean that kind of while. So basically it is not, it will not get stuck like this. So deadlock is not, it is not a semicolon, right? It will not get stuck like this. So that's why we need to check carefully. Okay. See, let's just check for the deadlock. So if both of them are true, then both can get enter in the critical section simultaneously. So that's why mutual exclusion is definitely not satisfied. So it is actually not semicolon. Okay, that's the trick here. I mean, trick in the sense that this is how they are implementing. So if both of them are true, actually, then it can get entered into the critical section. So mutual exclusion is definitely not satisfied. What about the deadlock? Can it go in the deadlock? Let's just check. So deadlock means that it should be false. It should be false, and it is inside this while again and again, right? It should be false, and this should also be false. I mean, both of them say that okay, I'm false, and both of them are going again and again this while loop. Is this even possible? No, right? If this is false, it is possible that var q is false, but it is also possible that var p is false. But the moment you come here, var p is definitely true, right? Var p is definitely true. So basically, it is not possible that okay, both of them are false, and it is always false. It is not possible. The moment you execute this, it will be true, right? And then it will get enter. See, it is not possible that both of them are always false. Because if this is false, maybe it is false, let's suppose, and this is also false. It is not possible that okay, you can since it is false, then it will not go into the while loop, but because of this while true, it will keep on entering, right? Keep on looping. But it is not possible to always make it false, because anyway you are making it true. Then it will get enter. So deadlock is definitely not possible. Okay. So mutual exclusion is not there, and it prevents the deadlock, obviously, right? So the proposed solution prevents the deadlock but fails to guarantee mutual exclusion. So hence A is the correct answer here. Okay. So this is another question that we have solved regarding the mutual exclusion, deadlock, progress, and these things. Let's just solve this question which has been asking GATE 2016. Okay. Again regarding the same things. Let's just solve this question. So what they are saying is that this is process 0, this is process 1. They are again asking bounded waiting, progress, mutual exclusion, these things, right? So maybe you can try this question. Let me just paste this question on the next page. Maybe you can try this question, right? Okay. Tell me, for this question, tell me, is mutual exclusion satisfied? This is entry loop while. Okay. So this is loop entry, this is loop exit. And this is a semicolon, right? Okay. I mean, this is not loop entry. This is critical section entry. This is critical section exit. Okay. This is pseudocode. So basically, what is the initial value of turn? Is initialized to 0. Okay. Since it is initialized to 0, that's why it is turn, right? So one of them will get enter, I think, right? One of them will get enter. Either turn is 0, turn is 1. So I think mutual exclusion is satisfied. What about progress? If one wants to come, can go? If turn is 0, can go? No. So progress is not satisfied because it seems to be strict alternation, right? Now what about bounded waiting? One of them you keep here. One of them you keep here, which means turn is 0 maybe. Okay. So turn is 0. One of them is a critical section. Another one is here. Another one is here. Another one is here. Now, can it go out? Turn will be 1. And then can it get re-enter again? Turn equal 1. It will get stuck, right? So bounded waiting is satisfied. So mutual exclusion, bounded waiting satisfied, but progress not satisfied. So this solution abolished mutual exclusion, no. Progress is abolished progress, right? So C is the correct answer. It is not a correct two process synchronization solution, okay? So C is the correct answer here. Let me know if you have understood this. Let me know. Okay, great. Now, let's just see Peterson solutions, which is the popular and the working solution. See, if you remember how many attempts we had, how many attempts we had? We had 3 attempts. And then if you consider these questions also attempt, okay, see, we had 3 attempts, that I agree. Then I think we have seen some questions. So basically this was the third attempt, right? Yeah, this was a attempt 3. This is attempt 3, and then we have seen some questions. So if you consider these questions also an attempt, because attempt is just whatever you want to do, right? So here also it was not satisfying everything. So maybe you can consider this as attempt 4. Okay, let's just consider this as attempt 4. I mean, 4 solutions maybe we have seen. This was, let's suppose, 5th one. Okay, this okay, we have not solved it. This was, let's suppose, 6th one. 6th, right? And this is 7th. So anyway, we have seen 7 examples. Okay, maybe somewhere some example might be repeating. So 5-6 examples we have seen, and none of them was working, right? None of them was working. So this is the first working solution for 2 processes. Okay, this is a working solution for 2 processes. Let's just see. Now, so if you remember from our attempt 2, if you remember, it was a strict alternation, right? It was a strict alternation. So you were saying that, okay, either this will go or this will go. So it was not satisfying the problem, the progress. So progress here was not satisfied, right? Okay. In the attempt 3, we have seen here also not satisfied. And what was the reason? Here also not satisfied because of the deadlock, right? Because of the deadlock. Here not satisfied because the strict alternation. There was no deadlock here, but because of the strict alternation, progress is not satisfied, right? So because strict alternation is there. Okay. Yeah, some of the students are requesting for memory management. Yes, definitely we will have memory management also. Okay, as a marathon. Now here the deadlock is there. Why? Because both of the processes may get into the while loop. I mean, may get stuck into the into this while, right? May get stuck into this while. Both of the processes may get stuck into this while. Okay. Now let's just see this Peterson solution. It is having this bond that I was having earlier. It is also having one more variable, which is called favored variable. Okay. It is also having one more variable, which is called favored variable. What this favored variable says, it is just like that. Okay, let me just tell you that what does this favor variable says. It is basically a polite way to allow other process. What do I mean by that? Let me just tell you. See, just assume that there is a door. Okay, there is a door or gate or whatever. Let's suppose multiple people wants to get passed through this door, but at a time, let's suppose only one can go. Okay, let's suppose at a time only one can go. Now what you will do, if you are very very gentleman, okay, or the gentlewoman, so what you will do, you will say to other person that, okay, you go first, right? You will say you go, right? You go first, and this person may say you go first, right? And let's suppose that whoever is saying last, and it, or maybe first, whatever, right? I mean, that request will get accepted, which means they can say to each other that you go first or you go first. So see, tell me, are both are interested to go or not? Both are interested to go or not? Tell me. Both are interested, right? Still they are favoring each other, isn't it? So that is the purpose of these two variables, right? See, let me just tell you, we can verify whether it is satisfying all the requirements or not. But first, let me just tell you the purpose of these two variables. What is the purpose of want? It says I'm interested. It is like interest, okay? Showing the interest. I'm interested. Okay. It says it is a polite way of saying, polite way of saying to other process that you go first. Let me know, is this understood to everyone? Let me know. I mean the meaning of the variables, okay? We will see how it is working. But it is a polite way of saying that you go. It is saying that I am interested. So how the solution is working is very simple actually. Okay, very simple solution. Let's just see how it is working. See, here it will set it to be true. It will set it to be true, right? So let's just check. Let's just check if favored is not there. Okay, if favored is not there, which means let's suppose I'm saying to you, let's suppose the favored is not there, which means maybe okay, too blurry. Okay, so let me just maybe do one thing. Let me just assume that favor is not there. So maybe I can just erase this, right? I can just erase this. Let's suppose favored is not there. If favored is not there, in that case, can you tell me, isn't it the same solution that we have already seen? The same kind of solution? Isn't it the same kind of solution? Which means isn't it the attempt 2 or 3? I think it was attempt 2. Do you remember in the attempt 2 we had the deadlock? Or attempt 3 we had the deadlock, right? If favored is not there, then we are having deadlock. Okay, if favored is not there, then we are having deadlock. So which means if I do not have favor, that we have already seen, this is not a Peterson solution, by the way. So maybe I can just remove the heading for now. So it is not a Peterson solution. We have already seen this solution, and we have said like here the deadlock exists. And now suppose I am saying that in the Peterson solution deadlock does not exist. Suppose I am saying to you, so if you're adding favor, then it help us. Okay, it help us to prevent deadlock. Prevent deadlock. Let me know. Is this understood to everyone? So this is basically what I'm saying, that see, currently you might not know that what this Peterson solution is. So let's suppose I'm telling you you satisfy all the conditions. Okay, we can definitely check, it's not an issue. But I'm just trying to make you understand that earlier we were having deadlock, but because of this favor we are not having the deadlock. Okay, it is just something I'm telling you. Currently I have not proved it. Okay, don't worry, currently I have not proved it. Take it as my words only, that I'm telling you that okay, because of the favor the deadlock is prevented. Okay, this is something I'm telling you. So this favored is basically very nice thing, isn't it? So how it is working, let me just tell you. See, earlier what we were saying, that if I want to go, I want to go. Okay, 1-0 is true, matlab I'm interested. 1 true, it means I'm interested. Now both are interested, both will get stuck, right? But if I have favor, then what it is saying that see, I'm interested, and this favored equal to 1 means I am favoring first, process 1. Okay, so which means although I am interested, but I am favoring the other process. Okay, it is just saying okay, you please go. See, it's like that. It's like that. See, I am interested, but it is just saying you may please proceed. Okay, it is saying you may please proceed. And let's suppose it is also saying you may please proceed. So So who will finally proceed? Okay, you just tell me, is this a deadlock? Will they keep on saying? Which means what I'm trying to say here is that is this favored? Is this favored? Is this inside some while loop or something that okay they will keep on favoring each other? It is not inside the while loop, right? I mean the assignment at least is not inside this while loop. They will not keep on favoring. So which means if I am saying you go, he is saying I go, then ultimately who will go? Ultimately who will go? Tell me. Wherever this favor turned out, see, both are interested. It's not like I'm not interested. I'm interested. Definitely I'm interested. So see here what is happening. See, see, it will check if you are interested and I'm saying you go and I'm saying you go, then I will wait. Okay. If you are interested and I'm saying you go, then I will wait. Let's suppose both are interested. Okay, both are interested. And then finally let's suppose favored is 0. Okay, maybe because it has been executed and after that it is executed. Both are interested, finally favor is 0. So this is yes, this is interested, finally it is favored, right? Since it is favored, right, whoever got favored, so it will say okay, I just got favored, that's great, so I will execute. So whoever is finally getting executed, it will ultimately get favored, right? It will ultimately get favored. So basically this Peterson solution is saying that see, both are, let's suppose both are interested. After this line, it may so happen that both are interested. Now whoever is favoring at the at the end, which means that whoever is updating the last, okay, it will get favored and it will say okay, you favored, let's suppose got 0, right? So it will say that okay, see, now I finally got favored, so I will get enter. So this favor is very nice thing which is helping us to prevent the deadlock, isn't it? Now let's just see. I mean, this was just one intuitive explanation, but let's just see theoretically that is I mean you can start with anything. Maybe let's just start with progress itself because earlier it was a problem. Tell me, is progress is satisfied? If one process wants to go, can it go? Let's suppose it is not interested. Another process is false. This is false. Since this is false, then one process can definitely go, right? Because the end will be false. If both wants to go, if both wants to go, earlier it was stuck. Now tell me, will it get stuck here? Will it get stuck here? You just tell me. No, right? See, earlier if you talk about the thing, then earlier it was stuck. But now it will not get stuck, right? Okay, okay. So now I hope you understood that it will not get stuck. So basically, what I'm trying to say here is that this favor is very nice thing. This favored variable is very nice thing. It is saying that earlier we were stuck, but now it will not get stuck. So progress is definitely satisfied, right? Progress is definitely satisfied. What about bounded waiting? Maybe you keep one of the process in the critical section. It means want 0 is true, favored is 1. Sorry, favored will be 0, right? I mean favored will be 0. If this is in the critical section, that it means that it must be favored. So favored is 0. This is true. Now if it is waiting, then want 0 is true and favored is 0. That is the only reason it is waiting, right? So this process is waiting. This is in the critical section. Now tell me, can it go out and can go enter again? So then once 0 will be true, favored will be 1, right? Favored will be 1. So once favored will be 1, once 1 is already true, right? Once 1 is already true because other process is here, right? Once 1 is already true actually. Okay. This is already true because other process is here. So now you tell me, can it go out? Once 0 will be true and favored is 1. So once 1 is true and favored is 1. Since it can't go and come, come again, hence bounded waiting is also satisfied. Right? What about deadlock? What about deadlock? Tell me. What about deadlock? See, not deadlock. What about mutual exclusion? Mutual exclusion. What about mutual exclusion? You just check. Can you ask both of the processes? The answer will be no. Actually, the answer will be no because of the favor. Actually, the favor is saying only. If you are inside, then favor must be 0, right? I mean, you can check it, right? If both the process wants to get enter, then let's just check if it is allowing. If it can allow both of them. See, want 0 is true, favored is whatever is favored, it will allow whoever got favored at the end, right? So that will get allowed. Okay. So it can't let enter both of the processes at the same time. So mutual exclusion is also satisfied. So mutual exclusion, progress, and boundary waiting, all of them are satisfied because of just this favored. Okay. Just one more variable we have introduced rather than the last variable. So I mean, at last we left it with this thing, right? This was attempt 3, right? But now in the Peterson solution, I just added one more variable which is favored, or maybe if you talk about Galvin, then they call it, I think, turn. I mean, whoever whatever you call it, it is turn, favor, whatever. But I thought the favored might be a good thing to understand, so that's why I named it favored. But anyway, that is fine, whatever you name it. Okay. So that's how the Peterson solutions will be working. Now, let me tell you one thing. See, you will not find this kind of explanation of the Peterson solutions at most of the places. Like, I'm almost sure that it is very difficult, okay, at other places to explain this Peterson solution variable meaning itself. See, we have basically explained this favored variable in very nice way, that it is a polite way of saying that, okay, other process you go. This is not easily accessible to other places. That is, I'm sure of. Tell me, have you seen this kind of explanation to other places? Tell me. Okay, at least I have not seen. And also, let me tell you one thing. See, do you remember when I was motivating the idea, right? I was motivating the idea of this critical section. Then I said that, okay, maybe we can start with the mutual exclusion, and then we said, see, if we just have the mutual exclusion, then we can have while one both the places, and mutual exclusion is satisfied. That's why it is a horrible solution. Okay, just mutual exclusion is not good. So what I'm trying to make a point here is that at almost all the place, you will directly see one of the slide. Okay, you will directly see that, okay, for the critical section, you need mutual exclusion, you need progress, you need bounded waiting. You will directly see this slide or this particular presentation. They will not motivate the idea that, okay, if you just have mutual exclusion, okay, then what is they will not motivate the idea that, okay, see, I motivated the idea like this, that, okay, at the first glance, okay, the straightforward solution says that comes to our mind is mutual exclusion. So we have motivated the idea like this, and then we said that, see, alone mutual exclusion is not enough because it is a horrible solution. Then we have motivated the idea that, okay, there should be some extra conditions, right, other than mutual exclusion. So there should be some extra conditions. Okay. Now, what are those extra conditions and why we even need it? Okay, that should be clear. Why we even need it? Because mutual exclusion alone is horrible, and extra condition means that at least some progress should be there. Then we took an example of prime minister and this particular persons wants to meet. Then we said that, okay, mutual exclusion progress means exactly one, but this is also not enough because one process can go and come again. So basically all of these conditions, which is mutual exclusion, progress, bounded wait, these things we have motivated, not just presented it. Okay, we have motivated this idea. Let me know if you have completely understood this. And then finally I told you a systematic way, okay, from University of Otaha, a systematic way to check these three things. And then we have very easily related that how this Peterson solution is working, right? Using the favored variable, intuitively meaning, right? It is basically, see here in the Peterson solution. See, in the Peterson solution, it is this favored variable is just a polite way of saying that, okay, you please go, right? Something like that. So now I hope this Peterson solution is clear to everyone. Now let's just see what are the disadvantages of the Peterson solution. This was so you might say that, okay, I'm not very optimistic, or I'm maybe pessimistic that this is very first solution that we have got. But we need to see that, okay, is this enough, or there are some disadvantages even. Let's just check, right? So there are disadvantages of Peterson solution. What are these? That the code is slow. Compared to hardware. See, if you have these kind of code or something, right? If you write these kind of code to the critical section, this is slow, right? Compared to hardware. There's a busy waiting. I mean, one of the processes is stuck in the loop, and another process is basically doing the critical section. In the sense that it is consuming CPU cycle. If you're executing this loop again and again, then it is consuming CPU cycle. So let me just tell you, the code is slow. Proving the correctness is also an effort. I mean, it's not easy to prove that okay, it is working. Okay, I mean, it is all of this is satisfied. Mutual exclusion satisfied, progress is satisfied, bounded waiting is satisfied. It takes an effort, right? Proving is an effort. It is the solution only for two processes, right? And also it is a busy waiting, which means it is basically wasting CPU cycles, right? So these are the disadvantages of the Peterson solution. Now let's just see hardware supported solution. So now we have completed our one type of solution, which was, what was the one type? See, I told you that we are going to see user written solutions and hardware solutions, hardware supported solutions. And what else we are going to see? Yes, operating system supported, right? This is basically called semaphores. So now let's just see hardware supported solutions. Okay. So what we can say that as per the hardware, we have two solutions, two kind of solutions. One is disabling the interrupt itself, which means I'm saying that there should not be any contact switch. Another one is special machine instructions. So let's just see disabling the interrupt. This is one kind of solution. Okay. Okay. So let's just see this kind of solution, which is disabling interrupt. So do you think this kind of solution is good? See here that if you are saying that okay, there is a critical section, and whenever you go into the critical section, you disable interrupt. You disable interrupt, which means that there is no context switch, there is nothing. I mean, you will execute it fully, right? It seems a good idea. See, if you are saying that okay, before, if you just see here this kind of solutions, if you are saying something like this, right? If you are saying that before enter into the critical section, you just disable the interrupts. Okay, before entering into the critical section, if you are saying something like this, that disable interrupts before entering into the critical section, in that case it is a okay, it is okay thing, but it is basically not a good idea. Why? Can anyone guess? Maybe it might be the case that someone goes to sleep. Okay, I mean, let me just tell you that what are the problems here. Okay, so see, if you disable interrupt, then first of all, I should not allow user to disable interrupt. Okay, I mean, user should not be allowed to disable interrupt. So anyway, there will be a lot of effort. So let's just see this paragraph. The critical section problem could be solved simply in the single process environment if we could prevent the interrupt from occurring while shared variable is being modified. So let's just see that working of disable interrupt. The critical section problem could be solved simply. Okay, that's what we have seen. In this way, we could be sure that current sequence of instruction would be allowed to execute in the order without preemption. No other instruction would be able to run, so no unexpected modifications could be made to the shared variable, right? This is from Galvin. Okay. Yes, deadlock is prevented in the Peterson solutions, definitely. Okay, because the progress is there. If progress is there, then deadlock is definitely, satisfied. Okay, so what are the problems with the disable interrupt? Can anyone guess? Unfortunately, the solution is not a feasible in a multiprocessor environment. First of all, why? Because there are processor. Let's suppose CPU one, CPU two, or something like this, right? CPU two. Then, if you're disabling interrupt here, then you have to disable. By the way, if you're disabling interrupt here, which means there should not be any context switch in CPU one, then you must be disabling first of all interrupt everywhere. Okay, then it is too much inefficient, right? Disabling interrupt multiprocessor can be time consuming because since this message to be passed to all the processor, so you must say that okay, I'm disabling interrupt here, then it must say to CPU2 that you also disable the interrupt. So there has to communication between the processors, right? This message passing delay entry into the critical section and each system efficiency decreases. So there will be obviously efficiency will get decreased. Also consider effect on the system clock if the kept updating by the interrupts. Okay, so don't worry about it. So let me just tell you from other resources also that what is the problem with the disable interrupts. So there are many problems with the disable interrupt. The popular one is that if it is multiprocessor, then it will be a lot of problem, right? So let me tell you from Tenenbaum that what is the problem with the disable interrupt. Okay, so can you read this paragraph? Can you try reading this paragraph? Okay, so what this is saying, this approach has some problem, right? The approach is greatly unattractive because it is unwise to give user process to power to turn off the interrupts, right? So basically that you can't just say the user to turn off the interrupts. So it is not a good idea to give that particular command to the user. What if one of them did it and it never turned it on? Okay, can you trust user? It may so happen कि it does it, okay, and it never turn it on, right? That could be the end of the system. Furthermore, if the system is a multiprocessor, then disabling interrupt affect only the CPU executed on the disable instruction. The other ones are continue running can access the shared memory. Okay, so other CPU can access, and Galvin is saying that if you want to disable on other CPUs also, then it will be time consuming, right? It will be time consuming. Okay. Yeah, busy waiting is not solved in the Peterson solution because it may wait in the loop. So you can understand that this particular, I mean, this is optional read from William Stalling. If you want, you can read it. So basically, what is the problem here? The problem is that we cannot, okay, we cannot trust users to disable interrupt. Trust users to disable interrupt. What if one of them disable and never turn it again, right? Is this okay to everyone? Second problem is that in multiprocessor environment, we need to disable interrupt on multiple CPUs, right? We need to disable interrupt on all CPUs, which is slow. Okay, because the message has to be passed that okay, disable. Okay, because that message has to be passed. I'm not writing that message, I mean the message thing, but I hope you understood. So these are the problems with disable interrupt, right? So see, I have taken from every every book which is relevant. So I have taken the paragraphs from the every book, which means Galvin, William Stalling, Tannenbaum. So if you want, you can read these. Okay. So I have taken this particular topic. I mean, many of the topic we have taken from these multiple books. Okay. Actually, in these books, this is the only paragraph regarding this particular concept. Okay, this is the only paragraph, right? Okay. Now let's just move to the next thing, which is atomic operation. So basically, these are the second type of the hardware solution, which is atomic operations. Okay. So what does this atomic operation mean? It says that what we can do. See, do you remember? Do you remember these solutions that we had earlier? Let me just walk you through the solutions that we had earlier. Okay. So for example, let's suppose that these are the basically, I mean, the problem is occurring because they see here here the interrupt may come, right? I mean, both of them can set true, and it is a deadlock, something like this, right? So basically what we want to make these things as an atomic. Okay, what do I mean by that? Let me just tell you what do I mean by that. So basically let's just assume this thing. Suppose, do you remember about attempt one at least? It was regarding the interested variable. Okay, I was checking while interested equal, let's suppose true, of okay, equal, maybe you can say false. Okay, or maybe let me say 0 or whatever, right? I think it was like this. Okay, interested, it was 1, and then interested to be 1. Initially the interested to be, we have set it to be 0, right? So basically you're testing here whether interested is 1 or not. If it is not 1, then you're setting it to be 1, right? But we have seen it was the attempt 1, but there is a problem here. So basically testing whether interested is 1 or not, and then setting the interested is 1, right? This is happening in two instructions, you can say, right? So this is test, this is set, right? What we want this test and set to be done in just one instruction. Okay, so that is why we take support from hardware, right? That is also called test and set instruction. Okay, so we will test whether this interested is 1 or 0. If it is 0, then it is good, we will test it and we will set it. So basically this test and set, we want it to be just one. Okay, one atomic thing, we want it to be done just one atomic thing. Okay, let me know, is the idea clear to everyone? At least we want them to be an atomic thing. If that can be done atomically, then basically it will solve our problem. I will show you how. So basically not just this test and set, there are many other operations. Okay, there are many other operations which are given to be here, and these operations are supported by different hardware. Some hardware support this instruction, some hardware support this instruction, some hardware support this instruction. Okay, now let's just see that what is this test and set. So see here, this is saying the software based solution are slow, so that's why Libre CPU atomic instruction like test and set. This is University of Illinois. So let's just see that what is this test and set, and how to have this test and set, and so on, right? So see here, the CPU provides atomic instruction. Okay, something like this. So this is the atomic instruction in the sense that this is just happening in just one go. So let me just tell you what do I mean by that. What it have. Let's just first see. It is saying that this flag variable, right? It will take this flag to be in the old. It will set it to be true. Okay, it will set the flag to be true, and it will return the old. Which means it is returning the old and setting to be the true. Which means once you call this test and set, it will set it to be true, but it will return the return value is the old value. Okay, let me just tell you that what does this mean. It says the old value to 1 and return the old value only. Okay, it will return the old value only. So basically what you are seeing on the screen is not exactly test and set, in the sense that it is not the way it is implemented. It is just a pseudo code I have written, but ultimately at the end of the day, okay, it is just like a hardware instruction. Just like you heard about the move, R1, R2, these things, right? These things you heard. Okay, these things you might have heard. So basically this particular instruction is just one instruction. Okay, it is just one instruction. Okay, which means this is just a example. It is not reality. It is not in real, it is implemented. Okay, see, note that above is definition, not the implementation. It is not how it is implemented. It is supported by the hardware. So basically in the from the Tenenbaum I have taken this test and set work as follows. Read the content of the memory, word lock into the register and then store the non-zero value. So basically, let me just tell you that what it does. Okay. So suppose I'm calling test and set like this. So suppose okay. Suppose this is process 1 or maybe 0 and this is process 1. Okay. These are the two processes. Suppose initial value of lock is 0. Tell me what it will do. This instruction will say test and set lock, right? It will basically do one thing. Okay, it is just a pseudo code. It will just do one thing. What it will do? It will say that okay, it will say that it will return 0 because it will return the old value of lock, which is 0. And now after this instruction, okay, the lock is actually 1. So lock is 1, but it is returning 0. So hence it is returning 0. It will get into the while loop. Is this okay to everyone? Let me know. See, let's suppose that lock is initially 0. Then what it will do? It will set it to 1, but return will 0. But it will return 0. Okay. Then it will come here, right? It will come here because it is returning 0. Suppose initially if lock is initially 1, then can anyone tell me what is happening here? Then it will return the old value, which is 1 only, and it will set it to 1 only. I mean, there's not needed to set, but anyway, that's how it works. So basically it will get stuck. Okay, get stuck. So if it is 1, then it will get stuck. If it is 0, then it will continue. Okay. I hope you are getting. If it is 0 initially, it will get changed to 1, but now it is continuing. I mean, because it will return 0 only. So that's how, I mean, this is just hardware instruction. Okay. And you don't have a pseudo, I mean, you don't have a code here. This is just a hardware instruction that you have to write in the assembly directly. Okay. Anyway, don't worry. Like I will just tell you that how does it work. Okay. How does it work? So now, yeah, thank you, Rohan. So Rohan is saying a top-notch explanation. Thank you so much, Rohan. So after this video, please just put a comment that how this video is helping you. Okay. Because otherwise it will not reach to many students. And the purpose of the Go classes is to reach to many students so that others also get to know about Go classes. Right? So that like all of this we are doing just to reach more students and just to help you guys. So if you just put a comment, then see, this is a normal tendency. Like if someone is coming to the video, then they just first look at the comments. If the comment is good, then only they will watch. Otherwise they will not watch. And also YouTube also recommend based on the comments. If there are more comments, there are more likes, then YouTube will recommend, right? Okay. So now let's just consider these two processes which are implementing test and set. Now you tell me, is this solution satisfying the mutual exclusion? Let's suppose lock is initially 0. Is this satisfying the mutual exclusion? What does the mutual exclusion says? Mutual exclusion says that, see, lock is 0. So if it is, see, it is atomic. Okay, it is atomic, by the way. So it will say that okay, I will set it to 1. I mean, I will set it to 1, but the old value is 0 only. It will return 0 only. So since it is atomic, it will happen all of them as just atomic instruction. So it will get enter. And now if at the same time if it wants to get enter, then it will say that okay, now lock is 1, then it will return 1, right? It will return 1. So basically mutual exclusion is satisfied. I mean, you can't ask both of them. You can't ask both of them. Why? Because if you are asking this one, then it will return 0 and it can get enter, but now the lock is 1 and this will return 1 only, right? So mutual exclusion is satisfied, definitely satisfied. What about progress? Progress says that if 1 wants to go, it can go. If 2 wants to go, then at least 1 is going. Yes. So that's why progress is satisfied. What about bounded waiting? Is bounded waiting satisfied? This is interesting. Tell me. You keep one of them in the critical section, which means lock is basically 1, and another one in the waiting area. Can it go out, which means lock is now 0? Okay, false, it is 0. Can it go out, can get enter again? Yes, it can go out and can get enter again. That's why bounded waiting is not satisfied here. Okay. So in this solution, you can say in this solution, mutual exclusion satisfied, progress satisfied, but it can re-enter again and again, which means one of the process can just wait here forever, right? So bounded waiting is not satisfied. Okay, okay, great. So that is why you will say that okay, these two are satisfying and one is not satisfying. That is fine, right? That is fine. Now, as you can see, this is a disadvantage of this, that however, there are some serious disadvantage. Busy waiting is employed. Okay, busy waiting means that one of the process can wait forever in this loop, right? I mean, it is no, this is not busy waiting. Basically, busy waiting in the sense that if someone is in the critical section and if it turns is coming, if this P2 turn is coming, then P2 is just wasting CPU cycle because it is the while loop. It got stuck in the while loop, right? So that is why you can say that busy waiting is there. Busy waiting is, I mean, busy waiting is there. It is not fully eliminated, right? So you will say that busy waiting is employed. Starvation is possible because bounded waiting is not satisfied, right? Bounded waiting is not satisfied. Hence starvation is there. Okay. That is why starvation will there. Let me know if you have understood this. So you can say bounded waiting, busy waiting is employed. Starvation means one of the process is starving. Okay, it will never get a chance. Starvation means one of the process will never get a chance, right? So you can say here that one of the process right. Okay. So we have seen couple of solutions. One of them is Peterson solution. What was the problem here? It was only for two processes. It can be implemented in the, I mean, this is the advantage basically. It can be implemented in the multi-process environment. Disabling internet not possible for multiple processes. It is actually difficult actually. Can be implemented any number of processes. So basically see, it was only for two processes. It is for any number of process disabling internet, but multi-process is not supported. Here it is supported, right? Test and set any number of processes. You can say, I mean, it doesn't matter that you have P1, P2, P3. Okay, any number of processes, any number of processors also. Okay. The only issue here is that it is a busy waiting. So the only issue which Akash was saying that it is having the busy waiting. So test and set has a big issue which is a busy waiting. No, bounded waiting and busy waiting is not related. Bounded waiting is something, it is saying re-enter. Okay. Bounded waiting is something, it is saying can you re-enter. Busy waiting is something, it is basically got stuck. Okay. Whenever it is getting a chance and if it is wasting the CPU cycle. Okay. If let's suppose, see, busy waiting is always there until and unless you put it in the ready queue. I mean, it will be in the ready queue. So basically, you put it in the block. You block the process. If you're not blocking the process, busy waiting will always be there. Using the semaphore, we can remove the busy waiting because we put it in the queue. Okay, we put it in the block queue. Using the semaphore, we can do it. Okay, so we will see the next solution, which is semaphores, which does not even have the busy waiting. I will tell you very interesting thing about the semaphore, that it has very, I mean, busy waiting actually it has, but very less. I mean, extremely less, and which is very interesting concept. And I'm sure that nobody I mean, teaches at least in the gate industry. Okay, it is just a 5-minute concept. Anyone who is a Go classes student who knows that in the semaphore where is the busy waiting and how it is actually solving the busy waiting program, still there is a busy waiting. Someone who is a Go classes student. Okay, it is just a 5-minute but extremely interesting concept. Okay, that how the semaphore actually get implemented, which is very important. Okay, anyway, now let's just see this test and set. There are few questions on this, and then we will see semaphore. Okay, so let's just see these questions. Now this question has been asked in gate 2009. Okay, this question has been asked in gate 2009. Let's just see this question, what they are trying to say. So they are saying, let's suppose this is given. This is how your enter CS implemented. This is how your leave CS implemented. I mean, I think this is exactly same like this. Okay. I mean, exactly same like this, which we have already seen. So I think we have already seen this, that bounded waiting is not satisfied, right? Enter CS is like this. If leave CS is like this, then bounded waiting is not satisfied, and mutual exclusion progress is satisfied. Anyway, let's just see the question itself. So what they're saying, in the above solution, X is a memory location and this so on. Okay, so they have said that what is this test and set, I think. Okay, they have not said it. Okay, test and set is a well-known instruction, so that's why they might not have mentioned it. Anyway, the above solution, the critical solution, is deadlock free. Is this deadlock free? What do you think? Is progress satisfied? Yes. Since progress is satisfied, then it will be deadlock free, right? Because progress guarantees the deadlock. So it is deadlock free. It is starvation free? No, no, no. The processes enter in critical section is in FIFO order. No, see, we are not maintaining any order that okay, who will go. I mean, there. In fact, it is possible that one of the processes can keep on re-entering because bounded waiting is not satisfied. If this is a FIFO order, then obviously the starvation free will be there, right? So no, more than one process can enter in the critical section at the same time. Mutual exclusion satisfied, right? So this is also no. More than one process, no. So I think A is the only answer, right? So A is the only answer. So basically, you can see here A is the only answer. Okay, we have already seen this. Let me know if you have understood this completely. Okay. Now let's just see this GATE 2012 question. Right? Let's just see this question. So what this question is saying, there is an instruction fetch and add. I mean, they have defined some instruction which is fetch and add. This instruction, let's just see that what this instruction is doing. Okay. So they are saying instruction that reads the value of the memory X, increments the value by I. Okay. So it will increment by I and returns the old value. Okay. It will increment the value, this fetch and add Xi, it will increment the value by I and returns the old value. It is used for the pseudocode shown below to implement the busy wait lock. L is unsigned integer, shared variable initialized to 0, the value 0 corresponding to lock being available. So they are saying L is a variable, which means if value is 0, which means lock is available. Right? If L is 1 or non-zero, let's suppose, okay, maybe it could be side 1, 2, 3 like this, then lock is unavailable. Sorry, available. Okay. Okay, any non-zero, since it is unsigned, so I'm saying 1, 2, 3. Anyway, so this is given. Now what they're saying, acquire lock and release lock is like this. Now what they're saying is that the implementation fails as L can overflow, fails as L can take non-zero values. Let's just see. Okay. Suppose this is my implementation, right? Okay, critical section implementation. So maybe in between there will be the critical section, but that's fine. So let's have multiple processes. Okay, so let's suppose this is the first process which is executing like this, second process executing like this, and there may be multiple processes executing like this, right? Okay, so let's just see this. Let's suppose this is P1, this is P2. There might be multiple processes executing like this, P10, okay, or P100 or whatever. Okay. So there will be the critical section. I mean, after this acquire and release, in between that there will be the critical section. So maybe you can say that in between there is a critical section, right? Critical section here, critical section here, critical section here. Now what will so happen is that you will execute this. You will say fetch and add L1. So let's suppose L is initially 0. Now if you are executing this, it will return 0. Since this is false, right? Since this is false, you will come inside the critical section, and now it will basically also increment it to 1. So basically you are inside here, right? P1. Is this okay to everyone? Because it was false, right? And this is atomic instruction. Now what may so happen? Now you are, let's suppose, executing this, then L may be 2, right? L may be 2, but immediately you are setting it to B1. So remember, whenever you are doing in the next instruction, there is a chance of preemption, right? There is a chance of preemption here. So it may so happen that L is 2 at this moment, but immediately setting it to B1, L, you may execute this, and L maybe 3, and then so on, right? I mean, because of this process, maybe 2, because another process 3, 4, 5, and if there are many, many processes, it can go on, go on, go on, go on, go on, right? If there are 10 processes, maybe L maybe finally 10. If there are 100 processes, L maybe finally 100. So it may reach to the very high value. Okay. Okay. No, dining philosopher problem, I don't think we will be having time, okay, to discuss today. So it like we will be discussing in the on the YouTube itself, but may not be today. Okay, may not be in this lecture. Let me know if this understood to everyone that what I'm trying to say. Okay. So basically here what I'm saying is that you will execute this L here. It will 1, it will be 2, 3, 4, and it can go on to the very large value. So it may overflow. Actually, it may overflow. It can overflow. But the only thing is that it fails as L can overflow. But the only thing is that generally there are not these many processes. Okay, generally see this is unsigned integer, so I'm assuming this is 2 power 32 it may be its value, okay, maximum value. So generally these are not, I mean, there is a limit on the of the processes. So generally these are not 2 power 32 processes. Practically speaking, I mean, actually they should mention it, but they have not mentioned it in gate 2012, but they should mention it that the maximum number of processes are lesser than 2 power 32. Okay, generally that is the case in all the practical implementation, that is the case, but that's fine. I mean, L can overflow, but that's okay. Okay. So let's not worry about it. About this, I'm assuming that L cannot overflow. Okay. The reason being is that there might not be too much of processes, two power 32 processes. Okay. How preemption if it is atomic? See, only this instruction is atomic. Only this instruction is atomic. This L equal to 1, and there is a gap between these two instructions. Okay. In this gap, there is a preemption. That is what you need to understand. Okay. See here. See, if you talk about this, then only fetch and add. This is atomic, right? Okay. Yeah, you have a good question, but this is only atomic. But the moment you do L equal to 1, before that only there could be preemption that is possible. Okay. Anyway, let's not worry about the possibility that it can overflow, because I'm assuming that it can't overflow. Okay. So let's not worry about this possibility. Now let's just check any other possibility here. Okay, what might so go wrong? What do you think? What might go wrong? See, this L equal to 0, ultimately it should tell you that lock is now available, right? It should tell you that lock is now available. But is this possible that you can override this L equal to 0? Can you override this L equal to 0? See, P1 execute, P1 make it 1, and then other processes, whatever they are doing, maybe 2, and then immediately setting 2 1, and the 2 1 immediately, right? Or maybe whatever they are doing, okay, 2 1 every other process is basically just stuck in this. Let's suppose every other process is stuck in this. I mean, that is definitely possible that it may be 2, then 3, then 4, and that is definitely possible. But after some point in time, it will 1 again, right? By one of the processor, right? So it will be 1 again. So what I'm trying to say here is that, is this possible that is P1 is entering, okay, let's suppose this is entering, this will make 0 to 1, and then whenever it go out, it will make it 0 again, right? But can you override it? See, it is making 0. After that you are executing, which means let's suppose you are making 0, and then you are executing one of them. Maybe P2 you are executing, right? Maybe you are executing with P2. Okay. Then you are executing this. Then it is fine. See, if this instruction get executed, see here that this fetch and add, okay? If this instruction, this fetch and add get executed whenever this lock is 0, then it will permit. Okay, I mean, that's a good case. Okay, which means if this fetch and add, if this get executed whenever lock is 0, it is a good case. It will permit it, right? It will say that, okay, lock is 0, then you go inside the critical section directly. Now suppose it make the log to be 0, and who can make the log to be 0? only the process whoever is going out. But by chance, if I lose this, suppose by chance if I lose this, okay, suppose by chance if I lose this, then is there any possibility to recover? Can anyone make log to be 0? Can all of these processes, anyone can make log to be 0? No, right? Why? Because they are only adding. They're only adding. Suppose, okay, I'm just imagining a case that you execute this fully, you make it log to be 0, but by chance something happened, and then even if you make it 0, okay, immediately it is getting overwritten by something, okay, let's suppose, okay, is this possible? The answer is yes. See, suppose you make it 0, but then you in the P2 you are here. In the P2 you are immediately making it to be 1. See, if after this 0 you are executing this while, okay, you are executing this while fetch and add, then it is a good thing because then it will allow, right? But let's suppose you are not in this fetch and add. You are here at L equal to 1. You are here at L equal to 1, which means you execute it, okay, execute it L to be 0, L to be 0, then immediately you are modifying to L to be 1, okay. Now the 0 is lost and L is 1, and no process can make it 0 again. Everyone will get stuck, everyone. Tell me, is this understood or not? Is this understood? So it can fail. Why? Because this L equal to 0 can be overwritten by some other process. So that is why, what is the answer? Fails as L can take a non-zero value when the lock is actually available. Yes, lock is available, which means there is no process in the critical section. Still it can take the non-zero value, right? So that is why it can fail. So how to make sure that it is working? You need to make sure that there is no preemption here, which means basically you make these two fetch and add L equal to 1 and L equal to 1 as 1, okay. I mean, this fetch and add L comma 1 and L equal to 1 should be just 1 atomic, okay, should be just 1. I mean, something like this. If it is something like this, which means after L equal to 0, it's not like that you are executing this and then execute this. If you execute all of them as ones, okay, all of them as ones only, probably you will get rid of this problem, right? What you need to do, maybe you can say, see, what is your intention here? Your intention is that, what is your intention? If it is non-zero, maybe you make it to be 2 or 3 or something and make it 1, right? I mean, I don't know why you want to increment it. I don't see there is any point in incrementing. So if this is non-zero, you just set it to be 1, right? Just like test and set, right? It could be just like test and set. If it is just like test and set, in test and set we are not adding to be 1 or then again doing this drama of making it to be 1 again, right? So if it could have been just like test and set, then it will work perfectly, right? Okay, you test whether 0 or not. If it is not 0, set it, right? And just like one atomic instruction. So here what is the problem? This L equal to 0 may get lost. Okay, you are saying L equal to 0 and then at this moment you are at this moment in P2 and then it is executing L equal to 1. Now you are not recoverable. Understood? Okay, great. So hence this B is the correct answer. See, this question has been viewed by many users on the gate overflow, 21,000 users. And also if you see the solution, that solution is also having 176 subvotes. It means that people are looking for this question. Okay, let me know you understood this carefully or not. Everything, right? Everything about this question, that okay, it is here in the critical section. I mean, initially it may be the critical section. Everyone can be between 2 1 2 1 like this, right? 2 1 2 1 or maybe 2 3 2 3 2. I mean, it will check 2 3 2 and then 3, then maybe 4, and then ultimately some of them will make it 1, right? So they're non-zero. I mean, they're non-zero, and then ultimately it is 1. And then it may so happen that L equal to 0. And then after that, if anyone is executing this while fetch and L, I mean, if anyone is executing this, then it is fine. But it may be possible that one of the processes immediately gets scheduled such that it is executing L equal to 1. Then it is possible, right? So hence it is possible that L is non-zero even though lock is actually available. So that is why this is the correct answer, right? Okay, so I hope you understood that how to solve this question. Now are we done? Okay, Are we done? Hardware solutions are fast, but starvation was the problem. Busy waiting is the problem, right? So we can solve almost both of the problems, right? Starvation, busy waiting, we can solve almost both of the problems using the semaphores. So you might have heard about the semaphores. I will talk about the semaphores, don't worry. You might have heard about this little bit. I will just ask you one question if you have heard about the semaphore, okay? In the semaphore, tell me where it is implemented. I mean, I'm not going to directly ask this question. I will first teach it, but I'm just asking to the people who have already studied this. See, where the semaphore has been implemented in the operating system. Is the operating system hardware or the operating system software? Operating system is a software. It means it is also the code. So the semaphore is also the code, isn't it? So this semaphore is there to solve the mutual exclusion problem. But if you see this S is also the shared variable, isn't it? So here also in the semaphore also we are doing S minus minus. So if you have already seen the semaphore, you just answer me one question, that how to protect this S minus minus race condition. Okay, how to protect this S minus minus or S plus plus race condition. This is very interesting question that almost none of the gate aspirants can answer. I mean, according to my observation. So if you are Go classes student, maybe you can answer, because we have discussed this in very nice detail in the class. In just 5 minutes I told you, and this is very important, very nice. Okay, gate may anytime ask it. Anytime gate may ask it. In the interviews also they may ask it anytime. That how to protect S minus minus and S plus plus itself. It's a very, very nice observation that if you want to make. Okay. Anyway, let's not worry about it now. We will talk about it, right? We will talk about it, that how to do it and how not to do it. We will talk about it. Okay. If you're using another semaphore, so Amit is saying using another semaphore. No, if you're using another semaphore, then again that another semaphore will be having the same problem, isn't it? Another semaphore will also be having the same problem. So anyone who can answer that, if you have seen semaphore earlier, otherwise don't worry about it, right? Okay. So by the way, let me know if you have understood all of the questions, all questions. If you have understood that why we even need these three requirements. Right? If you have understood why we even need three requirements, if you have understood, let's suppose if you have understood why mutual exclusion plus progress plus bounded waiting, all of them are needed, right? Because these two, this alone is horrible, right? Because you can just say that, okay, nobody is going, deadlock. Okay, in case of deadlock also mutual exclusion is satisfied. So that's why you need to have the progress. But these two also are not making sure that starvation is not possible. That's why we needed to have bounded waiting. And all gate PYQs, right? All gate PYQs. If you have understood Peterson's solution very nicely. Okay, let me know if you have understood Peterson's solution very nicely. Let me know if you have understood everything. Okay, let me know if you have understood this particular question, which has got 176 upvotes on the gate overflow. If you have understood everything very clearly, then just put a comment after this video. We will see the semaphore and these things in the next slide, but I just request you to put a small comment. Okay, whatever you want. You just want to say awesome, you just want to say okay, you just want to say nice explanation, understood. Okay, you just want to say tick. Okay, you just want to say done, nice, whatever you want to say. Just one word is enough. Okay, if you want to write one line, this is good, but if you don't want to write one line, then just one word is enough for me. Okay, just do it after this video. Okay, it is just a request, and then we will have the semaphore in the next session. Okay, just a small request, just one word comment is also enough. Just do it, please. Okay, so that it get basically reached to many other students, and that is how we also get motivated, that okay, whatever efforts we are putting in, finally you are also helping us. Okay, so great. So we have solved all of this critical section problems, and now the very interesting topic, semaphore, producer consumer, this reader writer, dining philosopher, all of this will come in the next session. Okay, thank you so much. Thank you everyone. Take care. Bye bye. Okay, bye.